Hey, math people. So, made a thing. That thing is called the Preparation for Calculus Bootcamp, and/or alternative title, Precalculus, College Algebra, and Trigonometry Crash Course. It's a crash course. A lot of math in here. Get ready. This is going to be a long video. You probably already saw it when you clicked it. All right, so the situation is this. I'm going to scroll through and talk. If you are looking to take a calculus class, this video is meant to serve as a baton pass between, I don't know, high school math to calculus. Or maybe you're just studying pre-calculus topics or college algebra topics and some trigonometry, right? I got you. The crash course is for anyone that needs it. In terms of what it covers, so what I've done is this. I've been teaching calculus now for 5 years, and I've been a teacher for 10 for a while now. And what I've noticed is that what is most commonly missed in a calculus class isn't necessarily the calculus, it's the cumulative aspect of all the other math courses that came before it. We're talking Algebra 1, we're talking advanced and trigonometry, and I mean, even topics in pre-calc. Pre-calc is a little bit of a culmination between a few of those things. And there's a brief amount of geometry as well. So that's the intent of this video. I'm going to just go through the topics real fast, so that way maybe you can figure out which ones you need to watch. I suggest watching all of it if you are serious about taking calc and not making any simple errors that you could have fixed ahead of time. So chapter 1 is on lines and linear equations. So it's just power of 1. And then I said, hey, take that power of 1 and make it a 2. Crazy idea with the parabolas and quadratics. Then we got general polynomials, so make that 2 a 3, then a 4, then a 5, then a 6. Yeah, that's it for that. Then rational expressions, try dividing polynomials. So we got some asymptote action here. And then I say, okay, throw away with the natural numbers and introduce the rational exponent. So we got basic exponent rules and radicals, to follow. Then we have the basics of functions. So this just like function inputs, function outputs, composition of functions, transformations, piecewise functions, inverse functions, stuff like that. It's commonly found in like a little bit in Algebra 1, a little bit like in an advanced algebra course. Some exponential functions and logarithms. Those are inverses of one another. Of course, some trigonometry, right? We wouldn't be any fun without that. Some additional function concepts, which are kind of just like my odds and ends to try to make this exactly 10 chapters, because then the last one is just some light geometry that you need to know for calculus. All right, yeah, yapping. So without further ado, let's get into some, I guess, lines here, some pre-calculus. Go. Starting off the top with number 1, use either slope-intercept, everyone's favorite, or point-slope, which is even better. To write the equation of a line, you might use the slope formula as well, based on what you're given. So if you're given what is explicitly the y-intercept, 0, 4, this isn't just any old point, it's the y-intercept. And you're also given the slope. This is plug and play into mx plus b, right? 1/2 x plus 4. Life is good. But when you're given not a y-intercept, in fact, this is an x-intercept because the y value is 0, you have to plug and play into point slope. It's not that crazy of an idea. We have our x1, which is this 2. We have our y1, which is this 0. And we have our slope, which is 4. So we're just going to plug and play into that. And actually, that does get to kind of, there's a lot of conventions within calculus. So I will be just mentioning those as I go along. And a lot of these problems also have additional stories to them on occasion, so I might be trying to teach like a side lesson or a norm within the calculus course or something. So anyway, you don't have to always convert this into slope-intercept. You might feel compelled to, but you don't have to. I like to just keep it as is. You can even leave this plus 0 here, but if you feel compelled to, you're like, man, I can distribute that 4. Sure, 4x minus 8 is all the same. Okay, looking at C. So for 1C, we got a y-intercept and then just an arbitrary point. So I do have to use slope formula to figure out what my slope is going to be. So this is going to be my change in y's. So I'm going to do y2 minus y1. So that's going to be 4 minus a -1, and then all over 4 minus a 0. Good stuff here. So we get 5/4. That's my slope. And I have a choice. I can either use 0, -1, or I can use 4 to figure out what my equation is going to be. I think it's just easier to use the y-intercept, so I'm just going to do 5/4 x minus 1 to end that problem. For the next one, I'm just given 2 arbitrary points. This is common in calc, where you would have to determine both major important features of the line, the y-intercept and the slope, on your own. Not that crazy. So we're going to do exactly that. We're going to find that slope, and we're going to do 10 minus 5. So that would be that y2 minus y1, and then that's all over 2 minus a negative 3. So make sure to carry that negative over. So we end up getting 5 over 5, which can be simplified to 1. And I'm going to go ahead and plug into point slope now. And I'm just going to use, I don't know, the first point. Just don't want to have to deal with the 10, I guess. Although there might be good logic to use the second point, because you may not want to have to deal with the negative. But I want to show that. So if I have y is equal to, well, I have my slope is 1. You could put the 1 there if you want to, but you can kind of, leave it not there, and it's assumed to be 1. And then it's going to be, what is this? X. So it's minus x1. So this would be a minus negative to make it a plus 3. And then that's going to be plus 5 at the end. And here, I'll even prove that I can use the other point if I want to show that these are going to simplify to the same thing. For example, if I were to simplify this expression, it's just x plus 8. So if I were to write this using the 2 comma 10, it would be the 1 as well. Then what would it be? X minus 2 and then plus 10. Well, that simplifies to the same thing, right? You get x, right, 10 minus 2 last I checked was 8. Okay, so that's it for writing equations of lines. Oh, where's my cursor? Yeah, this is going to be a little annoying switching back and forth, but here we go. All right, so for 2, we got some special feeling ones. So go through the same exact motions as we did above, okay, but you'll see these will kind of feel a little different. So if I'm given, maybe I do actually want to keep the, gotta switch every time. Slope formula here. Okay, so let's go ahead and use slope intercept, right? Because I'm given what is actually the origin, but that's still a y-intercept, and then the slope of 1. So this is going to be y is equal to 1x plus 0. The reason why this feels a little special is that this is just y is equal to x, which is a common equation that we use like often in calc. Okay, so pretty much the same thing occurs with 2b. This is going to be y is equal to negative x. Same logic, just with a slope of negative 1. This one feels a little weird, but we can still go through the same motions. It's going to be y is equal to slope of 0. So 0x and then plus 0. So this is just y is equal to 0. When you have a slope of 0, well, okay, when you're on, say, the x-axis here, we'll write it that way. This is the same equation as the x-axis because all your y values are 0. X can be whatever it wants to be, but y must be 0. And then we actually get the opposite idea for part D here. Because you'll notice that you have an undefined slope. You can't quite go y is equal to infinity x and then plus 0. This doesn't feel right, so we're going to drive home the fact that we don't like this. What we do instead, we just write this equation as x is equal to 0. If you have an undefined slope, and it's like a wall, and especially on crossing through 0, 0, that's actually just the y-axis, where all your x values are 0, and y can be whatever it wants to be. So that's another important equation. Okay, keeping the party going here. With the next one, give you an equation of a line. And I say, what is the x-intercept? What is the y-intercept? So x-intercepts cross the x-axis. We'll do some highlighting. So it would cross through here. Hey, there it is. And then y-intercepts cross the y-axis. What? I swear I changed that color. Y-intercepts cross through the y-axis. It's easy to forget these things. I don't know. So sometimes you walk into calc and you're like, man, it's August. What's going on? Lines? I haven't graphed a line since 99. Anyway, so the x-intercept is right here. So that's going to be at, I can count, these go by 1, so 6, 7, 8, 9. So that's 9, 0. Not 90, 9, 0. And your x-intercept's done. For your y-intercept, that is at 6, so that's going to be 0, 6. And hey, look at that. That kind of makes sense. On the x-axis, we have a y value of 0. On the y-axis, we have an x value of 0. Full circle, or full line. Okay, what's the equation of this line? We can do that. So the y-intercept is 6. We've already established that. So I don't know the slope, so I'm going to just kind of say, I don't know, x plus 6 for now. And then we can find it. So I'm going to just, use that y-intercept, and I see another point right here. It looks to me like it's down 1, 2, and then it's right 1, 2, 3. Remember, slope is rise over run. So we're looking at a rise that's negative, right? Negative slope. So we're looking at -2, and then this is over 3. That's my run. So x values go in the positive direction. And this is a downslope, so it makes sense. Okay, what is the equation of the parallel line that intersects 3, -4? So yeah, eventually just understanding what parallel and perpendicular lines, what their slopes are in relation to a given line, and that's eventually going to be important. So if I figure out the point of intersection here, so it's going to be at 3, -4. I'm going to go to that. 1, 2, 3, 4. Okay, so I have this point, and I want it to be parallel, so I want it to follow the same exact slope. Okay, so I'm going to just do this slope in reverse from this point then. So it's going to be up 2, 1, 2, and then it's going to be to the left 3, 1, 2, 3. And hey, look at that, I have my y-intercept. And we're looking at this line right here. These lines look parallel to me. So it's going to be y is equal to, so in order for us to have 2 parallel lines, they need to have the same slope. So -2/3 x is the same, but our y-intercept is a little different. This would be a y-intercept of -2. So y-intercepts are different, but slopes are the same. Okay, what about the equation of the perpendicular line that intersects at 5, 7? That would be up here. All right, perpendicular creates a 90-degree angle. In order to do this with our given slope, is we're just doing opposite reciprocal. So if we know the slope is -2/3, the opposite reciprocal slope, the perpendicular slope, is going to be just +3/2. And how about we do this one in a slightly different way? We don't have to count to the y-axis. Instead, we can use point slope. I could have used point slope in part C as well. So I'm going to do that. I'm going to do y is equal to 3/2, and then x minus 5, and then +7. And I can leave as is. So I actually encourage my calculus students to leave things in point slope. You don't want to accidentally distribute that 3/2 and go, man, 3/2 fraction times 5. I haven't worked with fractions since '99. What? So the point is that you can leave as is. At least in AP calculus, they kind of encourage that on the FRQ actually. And every professor is different, so remember there's different conventions. Last one. Now set the original line. Okay, wait. I don't remember writing this one. Now set the original line in part B. Okay, this one equal to the perpendicular line to find the point of intersection. Okay, we can do that. We just have to work with fractions, which kind of sucks. So I'm going to do the -2/3 x plus 6. Well, if this is equal to y and this is equal to part D, this is equal to y, we can set each of these components equal to one another. 3/2 x minus 5 and then +7. So here I did have to multiply it out for the sake of this problem, but if there was just part D in isolation, it would have been fine. So I'm going to do that. I'm going to multiply this out. I got -2/3 x plus 6. This is going to be equal to 3/2 x. So 1.5 times 5. This doesn't come out pretty, so I'm going to leave it as -15/2. Just multiplying the numerators with one another. Technically, this denominator is 1. And then +7. All right. I can clear the fraction here by multiplying everything by the number 6. That would be the least common denominator of 3 and 2. So this should magically clear the fraction to make this problem a little more manageable. So we're going to rewrite it over here. Okay, so we got -4x plus 36 is equal to, that's 9, right? Because that would be 18/2, so that'd be 9x, and then minus, what would that be? -45, and then plus 42. 6 times 7, some days it's 43, right? Anyway, we get, today it's 42, the correct answer. And we're going to just combine like terms, right? So the way we solve linear equations, you try to get all your x stuff onto one side and you get all your other stuff onto the other. I'm going to move the 4x onto the right side, actually, because I just don't have to deal with the negative number. And then let's see, this is actually, so negative 45 plus 42, that's just minus 3. So then I'm just going to add 3 to both sides. So this is going to be 39 is equal to 13x. Final answer, x is equal to 3 when you divide both sides by 13. Divide by 13, divide by 13. There. All right, so we get an x value of 3. It says to find the point of intersection. So I'm just going to take that 3 and just plug it into the original, and I'll just do that kind of mentally. So I'll say, so the point of intersection is going to be at 3, comma. 3's would cancel, so it'd be negative 2 plus 6, so that would just be 3, comma 4. And let's see if that like makes sense based off of the graph that I've drawn here. So I want to do a perpendicular slope with this point right here, 5, 7. So I'm going to go down 1, 2, 3, and then right 1, 2. Hey, look at that. Not only do we got that perpendicular slope, but we got that the point of intersection as 3, comma 4, which is what we got going on here. Good to see, right, when the math checks out. That's another nice thing about calculus, and you know, when math is kind of done right, is that you can do it in many different ways. The point of this video is actually the exact opposite of like rote memorization. The point of this video is that I try to keep you on your feet with some of these problems, and I do the problems in different ways and explain it, you know, conceptually more than anything else, because that's more important than memory, because memory fades. All right, so we have 3, 4. It does say what happens when you try this with the original line and then the line from part C. Okay, so that's a really quick and easy thing to show. If I attempted to plug the two parallel lines equal to one another, right? So I did negative 2/3 x plus 6 is equal to negative 2/3 x minus 2. These little bad boys, they'll just cancel. You just get 6 is equal to negative 2, which is a big and not a thing you can do. There is no solution. These two lines do not intersect. It is the tragic love story of two lines that have everything in common, the same slope, but never meet. So here we have no solution, no soul. That's a funner way to put it. Okay, moving along. We got lots of linear equations to solve. Fun. So remember, the name of the game is just to get all your x stuff on the one side and all the other number stuff onto the right. And it's a scale, right? So you're trying to get, if you do something to one side, you got to do it to the other. All right, we're going to distribute on in this 5. So we get 5x minus 15 minus 2x minus 3, and that's equal to x minus 12. Combining like terms on the left side, you end up getting 3x minus 18 is equal to x minus 12. So this is where we move all of our x gunk to left and maybe all of our y, not our y, there's no y's here, all of our numbers to the right. So I'm going to do that. I'm going to subtract the x from both sides, and I'm going to add the 18 to both sides. So I'm doing 2 steps in one. You can handle it. So it's going to be 2x is equal to, what is 18 minus 12? That would be a good old 6, bringing us to a final answer of x is equal to 3 with the division of 2 both sides. You know when it does that. All right, next one. I can distribute the 2, or I can multiply the whole equation by 2. It doesn't. Or I can distribute the half or multiply the whole equation by 2. It doesn't matter. Distributing this half just seems kind of easy because these numbers are both even. So half of 2 is 1 and half of 4 is 2. What else is going on? I can solve for x by moving the x onto the right side and moving the constant onto the left. So I get 6, look at that again, on the left side, and then on the right I get 3x. Whoa! So dividing both sides by 3, you get 2. Okay, next one, distribute. So you get negative 2 plus x plus 4x minus 2, and that's equal to, careful, okay, this moment right here, you would be shocked, maybe not, to see many people saying, oh, 2 minus 2, that's equal to 0. That makes this side easy, it's just 1. No, your dear Aunt Sally would be unhappy with that. Come on, she's making your favorite beef stew tonight. You do this to her? So no, please excuse my dear Aunt Sally. PEMDAS, that's where that came from. I didn't make up some random Aunt of yours. Although I like to think that some people have an Aunt Sally, and they're like, how do you know? Okay, well, anyway, parentheses go first, then exponents, and then multiplication and division, then addition, subtraction. So these two are the last. These two are the very end, addition, subtraction, and then these kind of get their own. So the point is, we don't subtract these right away. We actually we multiply first. So we kind of run through the list here. I don't see, simplify what's in the parentheses, already kind of simplified. No exponents here. So we multiply. This is going to be distributed. So this 2 drops down for the ride. And this is a minus, what is this, 4? And then plus 2x plus 1. Okay, let's combine some like terms. I get 5x minus 4, and that's going to be equal to 2x minus 2 plus 1, so that's a minus 1. Cool. So hopefully you're at the point where you can kind of do some of this in your head. Linear equations aren't really the issue for calc students in my kind of experience. So I'm going to subtract 2x from both sides and then move the 4 onto the right. So this would be 3x is equal to 3, so final answer x is equal to 1. Okay, and then some kind of different things happen in this last little segment down here. I'm just going to divide both sides by 2 here because I can, and you can't question that because I'm doing what I think is best. But if you distributed that 2, that's okay. You end up getting x plus 2, and then something normal happens here. Thought something weird would happen. Subtract those 2, so I end up getting 2x is equal to x. Weird. That's okay, though. You just get x is equal to 0, and does that make most sense? Yeah, it does. Normal situation there. All right, E looks to be the same equation, just this 2 is gone, right? So this 2 is not there. Let's see how that maybe changes the problem out. And this time I'm going to distribute because I can do what I want. And that's, again, the beauty of math, though, is that it doesn't really have to have one way of solving it. Conceptualize. Concept before memory, always. And speaking of concept, when I got the same thing equal to the same thing, I can stop here. Because if you go through that rote process of, okay, subtract 4, subtract 2x, subtract 2x, you'd get 0 is equal to 0, which is just an inherently true statement. I could have stopped and noticed this immediately, and that would have been just fine. This is just true. In fact, this is just the same line on top of the same line, so this is infinitely many solutions. Sometimes teachers write IMS, sometimes teachers write all reals, the symbol for it. Sometimes people say all reals, sometimes people do infinity. I don't really like infinity because that one feels a little weird. Maybe infinity solutions, that one feels a little better. Okay, last one here. I'm going to distribute this 2, and then I get 2x plus 2 is equal to 2x plus 4. And hey, wait a minute. If you subtract the 2x from both sides, you get 2 is equal to 4. I just proved a new theorem. That ain't right. This isn't Terrence Howard, right? This is false. You like this true, and we don't like this. That's false. So in math, if you get a false statement like this, this is no solution, no soul. Sometimes you see like this, like an empty set kind of thing. Yeah. Okay. How we doing? Because we're only 1 down. We got 9 more to go. Okay, onwards to chapter 2. So raising that power to 2. Quadratics, right? Parabolas. We like these. These are still not too bad. We got completing the square, quadratic formula, vertex form, standard form, intercept / factored form, factoring. We love factoring. All right, enough of that. So let's do it. All right, we got ourselves a graph here. That's a parabola. And it looks like it's an intercept form or factored form or however you want to call it. It helps you find the x-intercepts quite easily. I'll actually just kind of highlight that right now. Here's your 3, and here's your -1. We'll explain why the signs flip a little later. Okay, so what are the x-intercepts? Well, hey, that's what I just kind of made a reference to. We have x-intercepts of a -1, 0, and 3, 0. Done with that. What is the y-intercept? Even easier. You can plug in 0 and do -3 times 1 to get -3, or you can just look at the graph. Here we're just getting 0, -3. And then the next question is finally like a quadratic-based question. What is the vertex? The vertex of a parabola is either the minimum or maximum. Here it is a min. And that appears to be at 1, comma 1, 2, 3, 4 negative, right? So it'd be 1, comma negative 4. All right, C and D are just kind of like fun things to like write it in different forms. So multiply the expression out to rewrite the quadratic, and then set it equal to 0 and solve. Okay, so we're going to multiply this out. We have not yet multiplied out a linear binomial times a linear binomial. And what you need for that is some FOIL. So that would be the older way that this was taught, is through first, outer, inner, last. The new age way of doing it is just box method, but some people can just handle distribution without some sort of fancy trick, right? I'll just do box for this one once and then never again. When we multiply the first by one another, we get x squared. When we multiply the negative 3, so the inners, I guess, would be this little side here. This would be negative 3x. If we did the outers, x times 1 would just be your x. And then negative 3 times positive 1 would be negative 3. So we're looking at x squared minus 2x if you combine the negative 3x and x, right? And then minus 3. X squared minus 2x minus 3. Awesome. It says to then set it to 0 and then solve, which is a little goofy. This is just my way of, I think, just kind of introducing the quadratic formula as an option. Because really what I would do to solve this quadratic is I would factor it. So I would just go back to where we originally were and then set each factor equal to 0. But I want to demonstrate quadratic formula here, which is one of a few different ways to solve a quadratic. The way the quadratic formula works is we have a leading coefficient here of 1, so our a is equal to 1. We have our coefficient in front of the x is negative 2. So unfortunately, yeah, you need to know the quadratic formula for calc in a lot of cases, unless you're taking a class where it's like heavily calculator based, then you can probably get away with it. So the linear coefficient is negative 2, and then the constant is negative 3. And I'm just plugging in a good old negative b plus or minus square root of b squared minus 4ac, all underneath the radical, all over 2a. So that would be a positive 2 plus or minus the square root of negative 2 squared minus 4 times 1 times negative 3. And then this is all over 2 times a, so that's just 2. So you get 2 plus or minus. Let's just simplify the radical here. So that'd be 4 and then plus, which is good. Minus would have been bad. We would have got a negative. So it'd be 4 plus 12. So that's 16. So, and the square root of 16 is 4. Awesome. We're on the right track. So you get 2 plus or minus 4 over 2. Sure, we can just find both of the solutions off that. So we'll do the positive. I could divide everything by 2, but whatever, we'll just simplify it. So 2 plus 4, all divided by 2. I mean, well, I can address a common mistake here. Please do not do this. Don't do that. You'd be surprised. You'd be surprised. So that breaks order of operations, right? Addition and subtraction occur after division, not at the same time. Anyway, so 2 plus 4, that's 6 divided by 3. Hey, there's your 3. And then 2 minus 4, so that's a negative 2. And then over 2, that's your negative 1. Look at that. I know where those are from. Those are from right here. Okay, complete the square. Yeah, so there's like one day in Calc 1 that you need to know completing the square. It happens once. So I felt compelled to add it just for that reason. But if you're like, man, I haven't completed the square since 99. Yeah, me neither. I do it once a year, you know. Okay, so completing the square. So I'm setting this equal to 0 still. And I already know where I'm heading. Oops, I already know where I'm heading. I know that the solution of this is going to be 3 and negative 1, so I should just get that again. The way we complete the square is we take our b value and we cut it in half and we square it. So we would take that negative 2, cut it in half to get negative 1, and square it, and we get 1. So this seems like a random process right now. Sometimes people also move this constant over to the other side, so I guess I'll do that right now. I'm going to leave a little space, and you're going to see why. So the idea is that if we were to make this a 1, something special will happen. Now remember the name completing the square. okay, because that's going to come into play in like 10 seconds. And if I add 1 to the right side, I got to add it to the left. I can't just add it to only one side. So I'm getting a 4 on this side, and that 10-second timer is ringing right now, because if I were to factor this expression, what multiplies into 1 and adds into -2, this is just x minus 1 all squared, right? Yeah, it's x minus 1 times x minus 1. You can do the little box method there if you want. Anyway, I'm going to go ahead and apply what is called square root method now. Take the square root of both sides. The true inverse of the square isn't the square root, but actually the plus or minus square root. So we're going to get x minus 1 is equal to plus or minus the square root of 4, which is 2. And here you go. You get your 1 plus 2 and your 1 minus 2. So that's 3 and -1. Okay, so that concludes my little mini rundown of all the graphing forms, and I don't know what we can do with all of them, I guess. And now we're just going to straight up look at some equations. Factor for a bit, then look at some equations, I guess. So factoring's still a thing, right? Actually, we've been looking at this expression. Maybe I'll just keep it kind of scrolled up a little longer and then scroll down. We've been looking at this expression for the last 5 minutes here. If I were to factor this, what multiplies into -3 and adds into -2, that would be -3 and then a +1, right? And so sometimes people do like a little box. I don't even know how to, this little crisscross thing for factoring. I just do it in my head. But I'd like to do this. Here, I'll just show you what I do. So I want to multiply into -3 and add into a -2. So this is how I factor. We'll use pink, better pink. Yeah, that pink. So here's my -3, and I don't know. We'll use this green here. Here's my -2. Always. So we always, with a trinomial, well, there's other cases, but for factorable trinomials like this, we want to add into the b value and multiply into the c value. So if you take -3 and +1, -3 times +1 is equal to -3, and they add up to -2. And if you're not convinced, what you could do is you can double check your answer by multiplying this back out if you'd like. We don't have to here because we've kind of seen enough of this expression, in my opinion. So I am done talking about x squared minus 2x minus 3 forever. Okay, so we also have this thing called difference of two squares. So the formula goes like this: a squared minus b squared is equal to a plus b times a minus b. You don't have to know that, though. Technically, you can think here, well, how many x's are there if there's none at all, and there's 0 if there's none? So it'd be x squared plus 0x minus 16. A little weird, but you can think to yourself, what multiplies into -16 and adds into 0? Well, 4 and -4, right? 4 times -4, you get -16. 4 minus 4, you get 0. So you get x plus 4 times x minus 4. You eventually just develop an eye for seeing difference of dots, difference of two squares, dots. But you don't have to. If you want to just fall back to basics, you can. Okay, looking for a greatest common factor is also a good strategy for factoring. I can see here these all are divisible by 2, so I'm going to factor that 2 out. So I'm going to get 2 times the quantity of x squared plus x minus 30. So what multiplies into 30 adds into 1? That would be x plus 6 and x minus 5. The last case, gross. When you have an a value that is not equal to 1, you got to do a slightly different thing. Some people guess and check, by the way. Like, they just sit there and they just go, well, I know one of them has to be a 2x, and I know one of them has to be an x, and I want to add into this 2 here, so maybe, I don't know, maybe this could be a +1, and I know this needs to be a negative, so maybe this is like a -2, and then they say, well, wait a minute, that doesn't quite work, guess and check, right? And like, oh, okay, -2 times +1 is actually -2, so, wait, maybe if this was a negative, this could be right. And then, you sit, you kind of just think and go, oh, wait, well, you know what, that actually does work. 2x times x, that's 2x squared. Then you get 2x times a -1. Oh, wait, does this work? No, these two need to switch. That's why it's called guess and check, people. There we go. All right, now we're cool. Now we're cool. So we get 2x squared, and then what is that? Minus 4x minus x, and then a -1 times a -2 is a +2. So cool. You could sit there and guess and check. I'm going to show you what's going to be called, I don't know. It's an older technique. It's just called like AC method. Multiply the A and the C times one another. And then you do the same jazz that we did over here. So, okay, you take the A value, multiply by the C value, you get 4. So what multiplies into 4 and adds into negative 5? Well, that's going to be a negative 4 and a negative 1, right? So then you would split the negative 5 x into, so this is an equal, 2x squared minus 4x minus x, and then plus 2. And then you would factor each group. So this is now called factor by grouping. So I got this little group here, I got this little group here. So I'm going to find the GCF of each of these binomials, and then I'll be kind of one step away. So the GCF of these first two is 2x, and I can divide out the 2x from both of these terms to get x minus 2. And the GCF of these next two, there is none, but the leading coefficient's negative, so how about we just pluck out that negative? So it's going to be a negative 1, and then, well, this would turn to a positive x, and then negative 2, or positive 2 divided by a negative 1 would be a negative 2. And then we take, where we notice that of these two terms, hey, they both have a, I don't really like using orange twice here. They both have an x minus 2 as a common factor. So I can factor out that x minus 2 now, and then I get x minus 2 times the quantity of 2x minus 1, which is the same expression that we had with the guess and check. So do your thing, pick your poison. Whatever factoring style works best for you, works best for me is usually what I say to my students. And that's like pretty universal. Like I don't think any calculus teacher says, hey, you can't factor that way. You got to factor my way. My way or the highway. No, none of that. Okay, I said I was done with x squared minus 2x minus 3. I guess not. So this is how I would really solve it, by the way. I would do x minus 3 times x plus 1, right? And we saw that earlier. And then I would set each of these factors to 0 using what is called the zero product property. And the zero product property just says that if I had, like, I don't know, if I had two numbers, a times b, and a was 7, what must b be? B be 8. What must b be in order for, and hey, there's that 8. In order for us to get a 0 here, well, it's got to be 0, right? And what if my a value was 100? What must b be in order to get a 0? Well, it must be 0. What if b was equal to 99? What must a be in order to get 0? Well, a must be 0. So one of the two factors must be 0 in order to equal 0. So it's either this one's 0 or it's this one's 0. And that's where you get the sign flip. Told you I'd explain it. We can add the 3 to both sides. We get the 3, and subtract 1 from both sides. We get the negative 1. So two solutions. Quadratics can either have 2, 1, or 0. Or, yeah, 2, 1, or 0. We'll just stick to that. Technically, you can have infinitely many, but that's only if you have the same quadratic on itself. A 2, 1, or 0, right? If you have a parabola cutting through a line, it's either on the line, misses the line, or cuts through it at some point. All right, so I'm going to do some more factoring. Remember, okay, so in order to solve quadratics, you got to set it to 0 most of the time. Sometimes you can get away with that, but here you got to set it to 0 if you want to factor. So I'm going to get 3x squared plus 30x plus 75, and this is equal to 0. I see a GCF. I'm actually just going to divide out the GCF rather than factoring it out because I can just get rid of that GCF. If I divide everything by the GCF of 3, I can end up getting x squared plus 10x plus 25, and that's equal to 0. Let's factor this. What multiplies into 25 and adds into 5? That would be x plus 5 times x plus 5. Cool. So it's just x plus 5 all squared. I'm going to take that square root. Sure, you get the plus or minus in front of the radical here, but positive and negative 0 are both just 0. So I get x plus 5 is equal to 0. Final answer, x is equal to negative 5. So this is just when the quadratic is just sitting on the x-axis. Okay, so real fast, I'm just going to show two ways of thinking about this. You can either think about it as when does your quadratic intersect this line? Okay, and it does. It's a little hard to see. I could have changed the windows, but deal with it. It happens, give me a sec, it's like right around there. Ah, okay. Kind of is graying out. It's just not happy. So you kind of have this parabola, and this line barely skims it for just one moment. And it only intersects once. But you can also think about it as, well, if you move the linear term onto the left side, the quadratic kind of just takes control. It's the leading coefficient. So I have my 3x squared, and then plus 30x plus 75. I'm just trying to find the y, the x-intercepts of this. And, this happens at -5. So you saw the last problem intersected at -5. And then this one, the x-intercepts at -5. So I don't know. Visually, that's kind of what's going on. Okay, here we can actually just solve by square root. Take the square root of both sides, and you get x is equal to plus or minus 1. So visually, this is just when does the parabola intersect y is equal to 1? Well, it happens twice, at an x value of 1 and an x value of -1. I don't mind if you leave your answer like this. Some teachers say, no, you have to separate them. Some say, no, you can't write it like this. If you're going to write it like this, you have to use solution set brackets. And then some say, no, you have to write them as two separate statements. I mean, I don't know. Just follow the conventions of your classroom, right? All these are fine in my opinion. This one's a little sketch, but the rest are fine. Okay, so for the next one, we are solving for x, so I'm gonna notice that there's no x term. Anytime there's no linear term, you can actually forego any factoring or completing the square or quadratic formula ideology, and you can actually just move. Let's watch. Just settle up. You can actually just move the constant over. You get 4x squared is equal to 9. I'm going to divide both sides by 4. I get a nasty improper fraction, but we're not worried about that because we leave everything as improper fractions in calculus. You do not write this as a mixed number ever. I get a lot of that in August. Just leave it improper. So mixed is, don't write it this way, but don't write it as 2 1/4. Because you're kind of telling me, oh, 2 times 1/4, awesome, that's 1/2. And it's like, huh? Is 9/4 equal to 1/2? No. Mixed fractions are good with day-to-day stuff, but math, we leave it improper. Anyway, blah, blah, blah. I'm going to go ahead and take that square root of both sides here, that plus or minus square root. So I get x is equal to plus or minus. Well, I can actually apply the radical to both the 9 and the 4. So square root of 9 is 3, and the square root of 4 is 2. So you can leave it as is, x equal to plus or minus 3 over 2. If you want to write 1.5, you can, but there's no need. Leave it improper. Okay, looking at E, I'm going to notice here that we have x terms. I want to set this equal to 0. So I'm going to move the 3x squared onto the left side. I'm going to move the negative 2x. I'm going to add 2x to the left both sides, and then I'm going to subtract 2 from both sides. Actually, this one's easy. You can just kind of cancel that there. So anyway, I end up getting x squared. So, and then I'm adding 2x to both sides. So minus x is equal to 0. They have a GCF, so I can factor out that x. Right? If they both have an x in common. And then I'm going to use zero product property to get x is equal to 0 and x is equal to 1. Okay, F, I want to show something that's important because a lot of students do this next move that I'm going to do in red to say, hey, don't do this thing. What I notice is students will divide out a solution. So if you were to be like, oh, okay, well, actually, I can just get rid of one of the x's and divide out an x from the problem, you get x is equal to 1, and you're like, hey, life's good. 1 works, right? 1 squared is equal to 1 after all. You missed a solution. You missed a spot. And what you missed is the 0, actually, because you'll notice that this equation right here is actually going to simplify kind of in the same way. If I subtract out the x onto the left side, so x squared minus x is equal to 0, hey, wait a minute. I'm actually going to get my missing solution. I factor out that x again, I get x minus 1 as the other factor there on the inside. So same story, right? I get x equal to 0 and I get x is equal to 1 because it turns out that 0 squared is equal to 0. So that was a missed solution. I divided out a solution. Be very cautious when you are dividing out variables because that can happen. Okay. All right, I'm telling you, there's a lot of these hidden stories here. A lot of these hidden stories that I see all the time in calc that I just embed in all these problems and the 300 problems that there are. Okay, quadratic formula time. I mean, probably, right? This certainly doesn't look factorable if I set this equal to 0. You know, you can multiply the 6 and the 2. Quadratic formula is the alpha and omega equation of quadratics. You can apply it to literally every quadratic, but why would you want to, right? If I try multiplying the 6 and 2, that's 12. So what multiplies into 12 and oh wait, is this factorable? What multiplies into 12 and adds into -7? I didn't mean this to be factorable. Oh, it might be factorable. -3? Huh. I guess it's factorable. I'm going to roll with it. So -3 and -4. Right? Yeah, because we can split -7x into a -3x, -4x, and then +2. Find the GCF here. So this GCF looks to be a 3x. So I'm getting 2x -1. And then if I find the GCF of this second one, I guess I can avoid quadratic formula. It looked very quadratic formula-ish to me. I'm going to factor out, what is this, a -2 here. So a -2. And this is going to be 2x -1. Yeah. Is equal to 0. And hey, look at that. So the 2x -1 times 3x -2. I end up getting... so I'll just set all this equal to 0 here. So this is going to be x is equal to 1/2. And then the other one, 3x -2 is equal to 0. This is going to be x is equal to 2/3. Is that right? Because it don't feel right. I mean, it feels right, but it don't feel right. So I'm going to go ahead and graph this. So 6x squared minus 7x, and then +2. I was trying to figure out when this guy crosses through the x-axis. I guess it happens twice. Yeah, look at that. So, all right. We'll use this as like a other learning moment. So a lot of assessments in calc are non-calculator. Right, calc doesn't use calculator. Interesting. Anyway, and the point of that is to assess your actual understanding of it. But if you have access to a tool, I say use it. We're really ultimately just trying to figure out, so once you scoot that -2 onto the left side, we're just trying to figure out when this thing is equal to 0. And I can just graph it, and that occurs at the x-intercept. So I see 1/2, and I see 6.6 repeating. So I see the 1/2, and I see the 0.6 repeating. It looks good to me. Okay, so the next one, this one I will have to use quadratic formula on, though. Because this is actually a fancy special equation that is fun to know, not a need to know. If I scoot over this x and this 1, I can actually set up for a quadratic formula. I can try to factor what multiplies into -1, adds into -1, not going to happen. I get a is equal to 1, b is equal to -1, c is equal to -1, so I do x is equal to 1 plus or minus the square root of b squared, which is -1 squared. So 1 minus 4 times 1 times -1, and then this is all over 2 times 1, which is 2. And I get this expression. I get 1 plus or minus, what is this, root 5, and then over 2. Well, 1 plus root 5 over 2. 1 plus. This is a fun to know. Don't skip because it's cool. And then this all over 2. This is called the golden ratio phi. So here's like a little, I'm flashing something on the screen right now, a little like rundown of why this value is important. It just is, I don't know, one of the transcendental constants that we adore next to e and pi. Anyway, don't need to know that for calculus, but you do need to know the quadratic formula. So maybe you might run into an unlucky moment where you have to solve an unfactorable quadratic without calculator, and in which case quadratic formula's got your back. Completing the square works as well, but I say I don't know, just avoid using it unless you have to. That's an easy one to forget. Okay, and then for part I here, if I take the square root of both sides, hey, wait a minute, plus or minus the square root of -1, that's plus or minus I. And we do you a favor in calculus, don't worry about it. Don't worry about I. Yeah, so we stick to real numbers in calc. So you can actually just say no real solution. You can say no solutions. I would understand what you mean. I prefer no real solutions, though. No real solutions, because there are solutions. They're just imaginary. Okay, and then that's it for quadratics. Yeah, okay, just looking at my notes, just a little writer's note. I did this on purpose, the completing the square moment here, because check this out. If I were to rewrite this x squared minus 2x minus 3, which I said I was done with, and I definitely wasn't. If I were to rewrite this, where the negative 3, I were to split that into, well, I liked that 1. I liked cutting that negative 2 in half and squaring it, right? So I got plus 1. And if I were to rewrite negative 3, where I have like a 1 there, 1 minus 4 is negative 3. This would allow me to factor this trinomial up front to x minus 1 all squared minus 4. And this is vertex form. And this helps you find the vertex quite easily. You can see here the vertex is at 1 comma negative 4. Hey, look at that, 1 comma negative 4. So the point of kind of doing it this way here, so I don't know, I'm going to highlight in a color I haven't highlighted in yet, orange. There's 3 different forms of quadratics. You have intercept form, you have standard form, and then you have vertex form. Okay, next up, polynomials. So classifying polynomials by degree and number of terms, this can be useful if you're talking to your teacher about math. It's just useful in conversation. You won't ever really have to identify it out loud because how often do you have to give a speech in math? Just to make it sound like you kind of know a little bit more math than I guess your neighbor. So the way we do this, so it says to classify by both degree and number of terms. What I'm going to do is I'm going to identify the leading coefficient in each of these, which would just be the highest power. Leading term. Let's do leading term as a whole rather than just leading coefficient. So the whole leading term is the term with the highest power. Here it's x squared. With b, it tries to be tricky, and it looks like it's going to be x squared, but there's actually, hey, look at that, a negative 3x cubed, so power of 3. It looks like it's just an x squared here. It looks like it's just an x here. This one's a really big long term. It looks like the highest power is this 4. And then here, of course, it's just one term, so it's just that x to the 5th. So it's by highest power, that's your degree, and then number of terms. So if something has 3 terms, that's called a trinomial, and if something's power 2, it's quadratic. So quadratic is the adjective to describe this polynomial, which is a trinomial. It's a quadratic by the degree, and then it's a trinomial by number of terms. Here, this is a cubic trinomial, still 3 terms, just a new power, right? This one is a quadratic binomial, because it's only 2 terms. This one is a linear binomial, right? Because it's power of 1, not 2. Linear binomial. Over here, ton of terms, right? How many terms? 1, 2, 3, 4, 5 terms. We don't call it a quintinomial. We just call it a polynomial still at that point. So we're looking at power 4, which is quartic. You don't really need to know quartic. The ones I need you to know, linear, cubic, and quadratic. Quartic, yeah. So this is a quartic polynomial, and this is if you want to flex the next one. Power 5, quintic. I think it's quintic. I'm not going to look it up. Quintic, and then it's a monomial. That one you do need to know. Monomial. That's an N. Monomial. All right, for a single term. This could help in conversation. So if you're just talking to your teacher, like, hey, what do I do with this linear binomial again? They'll be like, all right, let's go. They know their language. All right, so this is the stuff you have to do. Very scarcely do I see too many issues here, but there is a common trap that I want to make sure we draw attention to. Okay, so adding, subtracting, and multiplying polynomial expressions. Let's do it. First one, adding, very straightforward. You're just combining terms. So sometimes people do oh, you can circle the squares, and you can box the linears, and you can well, don't forget about that negative. And you can put triangles around the constants. You don't have to do that. If you can just kind of see it for what it is, that's great. I see the x squared, so I do see two linear terms. 2x minus 4x is negative 2x, and then 1 plus 3 is 4. Okay. If you have a negative here, so for subtraction, you do have to distribute this to all three terms. So this is the same thing as 2x plus 1 minus x squared plus 4x minus 3. So it'd be negative x squared. I like to put it in descending, it's like standard form, descending order of powers. You don't have to. So this is negative x squared, and then plus 6x, and then minus a 2. Next one. Okay, so this is a binomial times a trinomial, which is not scary. Don't run away from me just yet. The way we do this is you can just distribute, right? You can just do this. Just distribute the 2x to all three terms, distribute the 1 to all three terms. So you're doing 6 multiplications in total. Or you can sit here and do what is called like a box method. This is optional. I'm just giving you strategies, okay? Just skip 20 seconds if you don't want this. Jeez. Okay, so the way that we do this, it's 2x plus 1, and then times x squared minus 4x plus 3. And then it just helps you visualize the multiplication, that's all. So this is 2x cubed. This is x squared, so I'm just doing multiplication. 2x times negative 4x is negative 8x squared minus 4x for this one. 6x, and then 1 times 3 is 3. Okay, so combining like terms, we end up getting a final answer of 2x cubed minus 7x squared plus 2x plus 3, right? Yeah, moving on to part D. Okay, this is a big moment in our time here together. Do not kill a cat. Relevant meme here. Don't do it. It is tempting, I guess, it's called the freshman's dream, by the way. That's how tempting it is. I think it has its own Wikipedia page. To distribute a square to a binomial. Ugh, don't do this. Don't do it. That's bad math. All right. If you have something like 5 squared, we know that 5 squared is 25 because 5 times 5 is 25. If you have something squared, you can expand the exponent through multiplication. So that's what's going on here. You actually have x plus 3 times x plus 3, and then minus, this on the outside, which is the cat-killed expression. So the answer here is not 0. What we can do is we can actually now distribute this properly. The x times the x, you get the x squared, and you're like, hey, that's the same thing. But then all of a sudden you have your outers and your inners that didn't get to meet before. X times 3x, it's a plus 3x. 3 times the x is another plus 3x. And then here's your 9. If you're subtracting off this, I'm going to distribute the square. So it's minus x squared minus 9. You get some cancellations here. 9s go away, the x squareds go away, and you're just left with 6x. So you'd be missing out on that 6x if you killed a cat. So don't do that. Okay, so next one. Let's distribute. So it looks like we gotta do that twice. Intentionally kind of confusing looking, right? X plus x is 2x. This is minus an x squared minus x, and then this is a minus x, and then negative x times negative x plus x squared. It looks to me like the x squares cancel, and then it's 2x minus 2x. Yeah, so 2x's just cancel as well. You just end up getting 0. Okay, and with f, remember not to do 6 minus 4 here. This is not 2, but instead you're distributing this negative 4 to both terms. So this is going to be 6 minus 4x squared minus 4x cubed. And then let's do some distribution here. So this is going to be plus 3x squared plus 3x minus x cubed, and then minus x squared. Okay, a lot going on. Let's do all of our cubic terms first. So that's minus 5x cubed. Then it's, what is that? A minus 2x squared, right? Because you have a minus 4x squared plus 3x squared. So it's a minus x squared, and then another minus x squared. You get minus 2x squared, okay? Feeling good. Then we just have one linear term, which is the 3x, and then as for the constants, we just have one constant. That 6 was here for the ride. I think that's it, so that's 9f. Looking at negative 5x cubed minus 2x squared plus 3x plus 6. Looking good. So yeah, easy to make like a small mistake there. Just a lot going on. Not a hard problem, but it's simple, but not necessarily easy. It comes down to making human errors. All right, so for the next one, 10. factor the polynomial expression. So there are some other factoring techniques beyond just quadratics. Sometimes you just have to factor out an x. There's grouping, and then there's also like a substitution within a quadratic. There is also, if you remember SOAP, same opposite, always positive for difference in sum of cubes. You don't have to know that for calculus, which is good news, so I'm not going to do it that way. I'm just going to do, you could see these factorizations. So for 10a, I see that you can factor out a negative 4x, so I'm going to do that. So I get x squared plus 2x plus 1 minus 1 minus a 1. Yeah. Well, I factored out the negative, so it'd be plus 1. Yeah. Anyway, this is going to be a long day. That's happening on the 3rd chapter. Geez. 7 to go, right? So I'm going to keep this negative 4x on the outside. I'm going to see what multiplies into 1 and adds into 2. That's going to be x plus 1 times x plus 1, so x plus 1 squared. This one, so you might see grouping where we've kind of already saw it before, but we didn't see it with a higher power than when did we see it? Yeah, we didn't see it with a power of 3. So I'm going to just do the same thing, just find the GCF of each of these binomials. So here the GCF is an x squared, and then on the inside you would have a 2x plus 3. And the GCF of these next two terms looks like it's going to be a 9, and I'm going to make it a negative because they're both negative. So it's going to be a minus 9, and then on the inside a 2x plus 3. Again, just kind of see what each of these terms have in common, right? They both got their 2x plus 3, so I'm going to be factoring that out. So the 2x plus 3 is on the outside, and what's left from the first term is that x squared, and from the second is that minus 9. We're not done yet. If anyone got their difference of two square senses tingling, you'll see here that x squared minus 9 is x plus 3 times x minus 3. So final answer, 2x plus 3 times x plus 3 times x minus 3. Said it faster than I can write it. Okay, the last scenario that you can run into is kind of like a substituted in quadratic. If you just like pretend, so if you see an x to the 4th, x to the 2nd here, you can just like pretend that this is x squared minus 2x minus 3. Oh, hey, look at that. We're not done with this expression yet. I told you it's coming back. Did I say that? I did not, but now I did, and here it is. I can just factor this, which we've already factored a number of times before. This is x minus 3 times x plus 1. So if you have a quartic, and then that second term's a quadratic, this would just be x squared minus 3 times x squared plus 1. Okay, we're done with that expression for real. All right, ending our factoring run here. We are moving on to finding real roots. Not an issue. So if you're given the graph, you're just seeing when it crosses through the x-axis. Here for this first graph, so I provide the graphs as kind of like a why do I provide the graphs? It's kind of a way to visualize what happens with our multiplicity, which I'm going to explain in a moment. But if you just have a simple case, a factor times a factor times a factor, you'll see, you know, this 1 is this 1 right here, this 2 is this 2 right here, and this 3 is this 3 right here. Remember, the signs flip because you're kind of like setting each factor equal to 0, right? You're setting x minus 1 equal to 0, you're getting that 1, so on and so forth, right? So the intercepts here would be at 1, 2, and 3. Nothing special happens here. But something a little weird happens within this next one. What you're going to notice, and this will come into play with finding intervals of increase, decrease, and concavity within Calc 1, is that if you have a power of 2, it's called multiplicity 2, which is an indication that there is what is called a repeated root. So for example, y is equal to x squared has only one real solution, and it's 0. But that 0 is repeated because that x factor, I guess, is being squared, which creates this like bounces off x-axis effect. So you'll notice with the linear terms here, x minus 1, x minus 2, x minus 3, for each of these, we cut through 1, we cut through 2, we cut through 3. And what's a little odd is that here we have a power of 2, and we don't cut through 2. We actually just like ping pong off of it. And this happens anytime we have an even multiplicity. If we have an odd multiplicity, pierce right through that. that axis, and then if it's even, then it's just going to kind of bounce off of it. So the last little note here is that there's something called fundamental theorem of algebra. So this is a cubic, so it has 3 zeros. This is 1, 2, and then 3, 4. There's 2 terms here, so this should have 4 zeros. But what you're going to notice is that we only cross 1, 2, 3 times because one of them is considered to be repeated. So the solution set here is -1, 0, and 2. You don't have to say 2 twice. You can. Some people do, but sometimes people just make like a note of that this is a repeated root. So eventually useful. Okay, what else is going on? So we just got some equations and inequalities, and then that'll be it for our polynomial run here. So I'm going to solve this one by moving the 64 over. And taking the cube root. So the inverse of cubing is cube root. So what times what times what is 64? Is how I want you to think about that. So just like how I feel like the square root of 9, right? 3 times 3, so that's 2 of them, square root 2. Here's cubic root, so 3. So instead of what times what for squares, it's what times what times what for cubes. So 4 times 4 times 4 is equal to 64. Another thing is you don't have the plus or minus here. So for evens, a negative times a negative is a positive. A negative times a negative times a negative is still a negative. If I attempted to plug in a negative 4 here, I just want to show you that negative 4 does not work. So, is this true, kind of? This would be negative 4 times negative 4 times negative 4. That's a negative 64. So negative 64 minus 64. Hey, wait a minute. That's not equal to 0. So the plus or minus comes into play for even. So again, you kind of see there's a theme with even and odd. It's going to happen a few times here. For even powers, when you're taking that even root, you need the plus or minus. For if it's odd, you just leave it as is. Okay, and then for b, you see it's even right there. So I'm going to divide out this 8. Why did I put an 8 here? I think I wanted that to be a 16. So for the next one, we have 16x to the 4th is equal to 625. If you divide both sides by this 16, you get x to the 4th is equal to, well, I don't know how to simplify that. I'm just going to leave it as is, right? 625 over 16. I'm going to take the 4th root of both sides. And so the 4th root of 625, what times what times what times what is 625? It's 5. 5 times 5 is 25, times 5 is 125, and then times 5 again is 625. So we're going to have a 5 in this. And then for 16, what times what times what times what is 16? Well, that'd be 2, right? 2 times 2 is 4, times 2 is 8, times 2 is 16. So the final answer here is plus or minus 5 over 2. Okay, for C, do not divide out that x. You will miss a solution. Instead, we will subtract the x. And we got a slightly different case of what we saw before going on here. X cubed minus x is equal to 0. Factor out that x, so you get x squared minus 1 as what's inside the parentheses here. And hey, you can factor that. That's difference of 2 squares, right? Those senses should be tingling at this point. We have x and then x plus 1 times x minus 1. And you get all 3 solutions, 0, -1, and 1. Okay, for our last one here, I'm going to move over all the terms. I'm probably just going to use some grouping. By the way, when you know what to do, you develop an eye for it, really, is the answer. It's pretty rare that you're solving any crazy polynomial that isn't one of these kind of like oh, you just factor it out and then it's a quadratic kind of thing. Or you're just taking a cubic root or whatever the root is that's necessary. You don't need to know a lot of fancy tricks for polynomials. Maybe grouping, but this is a bit of a stretch. So I'm going to move the 3x squared and the 24. So I'm going to get x cubed minus 3x squared minus 8x and then plus 24. Like, really, you're not going to probably be grouping too much in calc, unless your factoring style when your a value for a quadratic is not one. It requires grouping, then maybe, but. Okay, I'm going to go ahead and find the GCF here. This is an x, so this will be x squared. Oh, x squared is the GCF, right? Because the first term has x cubed, the second term has x squared. So I can take 2 x's out. So I'm going to have x minus 3. GCF of the next pair is a -8, so I'm going to get x minus 3. Hey, look at that. There's that match. So I'm going to get x squared minus 8 as a Factor, and then x minus 3 is a factor. I'm going to go ahead and set these equal to 0 now. I can use a very weird difference of 2 squares. So 8 is not a perfect square, right? So I can't really do difference of 2 squares here. You sort of can, but not with natural numbers, with whole numbers. So I'm going to just go ahead and set this x squared minus 8 equal to 0. This is x squared is equal to 8, and if you take that square root of 8, you can leave as is. You can do plus or minus root 8. That's totally fine. The other solution is 3. You can also simplify that root 8, simplify the radical. So you can split that into root 4 times root 2, which is 2 root 2. So you might see the answer that way on like a multiple choice assessment, but at least for the AP exam, and you know, things change, but it's been this way for a while now. If your answer is like numerically equivalent on the free response, then you can just leave it as is. But you know, some teachers may say you have to simplify that. Root 8, what are you doing? What are you doing, kid? You're gonna end up working at McDonald's with root 8. Get out of here. Get this root 8 out of here. You know, you might be in that conversation. So, okay. Why is it always McDonald's? That's like the negative one, right? What'd they do? All right, for the last one, so these are inequalities. Graphs could benefit you with inequalities. There it is. I'm trying to. Graphs can benefit you, but here we're just going to do them without a graph. Man, we can look at the graph of at least one of these, maybe two. So here we have 2x minus 14 is greater than or equal to 0. I'm going to move the constant to the right side. So 2x is greater than or equal to 14. Divide both sides by 2, and you get x is greater than or equal to 7. It does say to write them in interval notation, which is honestly the preferred notation style among students and teachers. You can do set builder, but boo, set builder. I ain't going to do it. Set builder is just like, I'll do it. It's just you do like little curly brackets and you say it's the solutions of x such that x is greater than or equal to 7. It just feels too pretentious, right? Interval notation, straightforward to the point. We're just saying everything that's 7 and then like forever after. We use a bracket on the 7 because it's an or equal to suggest to include it. And we don't include infinity. We use parentheses there because infinity is a concept and not a number. We can never, ever, ever put brackets on infinity. That's looking too brackety to me here, bucko. I need that to be a nice, smooth parenthesis. It's an ugly parenthesis, let's be honest. Okay, so the next one, I'll show the graph for this one just for fun, but what's going on here is you can factor. So you can get x minus 3 times x plus 2. And what we can do is we can do like a number line of sorts. So we know that the points of interest are going to be at a -2 and a +3 if you were to set these both equal to 0, right? And the idea is to plug in a number to the left of -2, plug in a number in between -2 and 3, and then plug in a number to the right of 3. This is how you do this problem without a calculator. And then I'll show you what it looks like on a graph. If I plug in like -10, this would be -13. So it'd be a negative and then times a negative, because that would be like a -8. So a negative times a negative is a positive. So it'd be positive on the left of -2. When I plugged in -10, I didn't know exactly what came out, but I did know that it was a negative times a negative, which is a positive. If I were to plug in 0, which is between -2 and 3, that'd be -3, which is a negative, times a 2, which is a positive. So positive times a negative is a negative. And then lastly, if I were to plug in something like 10, that would be like 7 times 12, which I don't know what 7 times 12 is. I'm not a human calculator. We just end up getting a positive value. Looks to me like we are positive to the left of -2 and to the right of 3. So when are we less than 0? Between -2 and 3. Non-inclusive, because it is not an or equal to. So final answer is -2 to 3. That is an interval, not an ordered pair. To show you what that looks like graphically, I'm going to do that. Graphically, okay, here it is. X squared minus x minus 6. We're just trying to figure out when we're, when we're below 0. So we're below 0 here visually from -2 to 3. The x values, right? We're answering it with respect to x. Yeah, so I mean, it's nice to look at a graph, but you may not have that as an option. Okay, for C, if you're dividing by a negative, you have to flip the sign. right? So here we're end up getting x cubed, sign flips, so you're kind of like, the problem's kind of like flipping, kind of. So you flip the sign. I got a video on it, you can look it up. Why did we flip the sign? Okay, anyway, so we get 16 divided by -2, so you get -8 here. And then can you take the cube root of a -8? You sure can, yeah. Yes, you absolutely can. Come on, get with it. We talked about this. Because a -2 times a -2 times a -2 is a -8, right? A negative times a negative times a negative is actually a negative. So we get x is less than -2, which will be from -infinity to -2. Don't include the -2, right? It's not an or equal to, so parentheses. Okay, and the last one. Okay, what we can do is a number line again. Sort of. Well, here's the thing, right? We talked about multiplicity. So we're gonna just connect this to why understanding multiplicity is helpful. We know that if you have a factor that is to an even power, it bounces off the axis at that point, and if it's to an odd power, it pierces through. So my potential intercepts, or not my potential intercepts, my strict x-intercepts are at 0 from the first term, 1, 2, and 3. Right? If you set each of these factors to 0, you would get these 4 solutions, right? So what I'm going to do is I'm going to notice here that the multiplicity of each of these is odd. So since the multiplicity is odd, I'm piercing through, right? I'm not getting this. So I'm getting an effect that looks like that. I'll show you the graph after. I'm getting an effect that looks like this. It's not bouncing off with multiplicity 2 there. So all I got to do is figure out just what happens when I plug in -1 that's to the left of 0, and then the signs will just alternate, which is good. So if I plug in a -1, this would be a negative. Okay, we can't juggle this incorrectly here though. A negative times a negative times a negative times a negative. So a negative times a negative is a positive. Negative times a negative is positive. So it should be a positive. So it goes bam, 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 bam. Okay, so when are we less than or equal to 0? It looks like it's from, so bracket, because it's a or equal to, 0 to 1 union. Oh, okay, so if your bracket, if your interval like is broken down into multiple pieces, then we use this U symbol to join the two sets together. So this would be the set from 0 to 1 inclusive on the endpoints, and then this would be the set 2 to 3 inclusive on the endpoints, because we have two separate sets that, you know, we don't want to include that 1 to 2, because it's positive there. Okay, I just want to show the graph, because it's kind of fun. So yeah, it's positive, then negative, then positive, then negative, then positive again. So we saw that, and you know, it's at 0, 1, 2, and 3. So we're below from 0 to 1 and 2 to 3. Okay, that's it for polynomials. All right, looking at rational expressions. Simplify each of the rational expressions below. Rational expressions are just quotients of polynomials. And then you get kind of funky stuff that happens because when you divide, you introduce this concept of dividing by 0, which creates an asymptote. So really that's the big thing that comes into play. And then just some simplifying things, some algebraic simplifications can be, yeah, I don't know. Sometimes students struggle with simplifying these expressions. Okay, so 14a is kind of straightforward, 25 over 5. This is just 5, right, by division. And then with the exponents, so we're going to do a whole section on exponents soon, but here we would subtract, right? So like 2 minus 3 is a -1, so you can bring that exponent down to the denominator. You can also think about it this way, x over x, or sorry, x times x over x times x times x. So you're just left with a leftover x down below. Okay, this is the moment. Don't kill a cat. Relevant meme. This is another cat killing moment. Don't do it. It is tempting. It is tempting to say this. 2x squared. No, don't do that. It's not how math works, right? So again, dear Aunt Sally's not too happy with that because division doesn't occur at the same time as addition, dummy. No, you're not dumb. You're a brilliant, beautiful soul. I just don't like calling people dumb. Anyway, the idea is we're just factoring out the x first before the cancellation, because of this, if I were to factor out an x here, what's left on the inside of the parentheses is 2x plus 1, right? They both have an x in common, and this is all over x. This is fair game, right? X over x, well, multiplication occurs at the same time as division, so that's fine. The final answer is 2x plus 1, right? So you wouldn't, for example, how silly this would be, right? You wouldn't say, well, okay, 25, that's 20 plus 5, and then over 5, 25 over 5 is 20. Nah, you ain't doing that. And you're not doing that with variables either. Okay, so likewise in C, you are not canceling out those x squareds, right? In fact, you are looking to factor. In a lot of these situations, factoring is going to be helpful for simplifying. So this is going to be x minus 5, and then what is that, x plus 2? Yeah, and then down below you have x plus 3 and x plus 2. So, you know, you have multiplication here. So these do end up canceling. And final answer is x minus 5 over x plus 3. Those x's do not cancel because Aunt Sally said so. All right, so the next one, factoring out that x, we end up getting x times x squared minus x minus 12, and that's all over, factor out that x over x squared minus 9. Hey, those are both factorable. So you get x times, what is that, x plus 4, and then x minus 3. And then that's all going to be over x times x plus 3 times x minus 3. And this always feels good, right? Boom, get out of here, out my way. This is my zone, not yours. And all those terms cancel out, all those factors cancel out. So I'm left with x plus 4 all over x plus 3. Lastly, with E, I don't know if your difference of two squares senses are tingling, but mine sure are. Not up in the numerator. Numerator is just what? X minus 1 times x minus 1. I could write this as x minus 1 squared, but I want to be able to see something. It's a little hard to see down below, but that is this difference between two perfect squares. It's just that the constant is, you know, the a value, and we're used to the other way around. So fine. How about you factor out a negative? And you make this negative x squared and then minus 1. You could do that, but you don't have to. You could have also factored in the way that it was written. But I'm going to just keep rolling with the way I wrote it here. I factored out a negative, and I made the negative x squared positive and the 1 negative, because then that negative is just going to be here for the ride now. And I'm going to get x minus 1 and then an x plus a 1. And hey, look at that. You get that cancellation of those x minus 1s. So you're left with just a negative on the outside of x minus 1 all over x plus 1. So if you have, like, say the fraction negative 2/3, that's the same thing as negative 2 over 3, or the same thing as 2 over negative 3, right? Just like how with rise over run, you were able to go, you can either go like down 3, well, in this case it would be down to right 3, or you can go up to left 3, because it's in the same slope, same direction. So, you know, another way you could write this answer, so maybe the purpose of this little discussion is maybe this isn't your exact answer, and what's actually listed is x minus 1, and then negative x minus 1 is maybe the multiple choice answer. So what this person may have done to simplify it is they wrote the negative down below. I'm just giving an example of like how it could be written, and then distribute. It could be written that way. These are all equivalent expressions, and one way isn't better than the other when it comes to these negatives. Okay, I know if you're taking the AP exam, sometimes the solutions for the multiple choice are like intentionally like algebraically like simplified, and maybe you mess up on that problem, not by the calculus, but by the precalculus, or by the algebra that leads up to it. Okay, so now we just have operations with rational expressions, starting with multiplication, the easiest one. This x plus 5 is technically a rational expression, sort of, but not really. I mean, it depends on how you want to be about it, because you can put it over 1, and then, now it's rational. It's like a fraction. It was always rational, but anyway, what that would allow us to do is that if we're multiplying two fractions by one another, so say, for example, to take 2/3 times, I don't know, 4/5. Multiplying fractions is straightforward. You would just multiply across the top and then multiply across the bottom. So same story here, multiply across the top. This is x plus 5 times, well, I can factor that, x plus 6 times x minus 6, all over. This factor is x plus 5 times x plus 6. And then we get some cancellation. The plus 6's go away, and the, what is that? That's a 5, right? The 5's go away, and you're just left with x minus 6. Okay, next one. Oh, okay, you may have heard keep, change, flip. Anyone, right? So if you're doing, again, you're dividing 2. So if you're like 1/2, and then now you're dividing, I don't know, 3/4. This would be the same thing, keep, change, flip, as doing 1/2 multiplied by the reciprocal. So it'd be like 4/3. So I don't know. Yeah, keep, change, flip. So this is the same thing as, and I'm just going to factor as I go along. The x minus 2. So I'm gonna keep the x squared plus 7x minus 18 on the bottom, but I'm gonna just factor it. So it's gonna be just algebraically equivalent. This is gonna be x plus 9 and then x minus 2. So I'm gonna do keep, change, flip now. So I kept the first one the same, algebraically equivalent. Change the division, which is kind of like a fraction bar, by the way, like numerator, denominator. I don't know if anyone knew that. And that changed the multiplication, and then I'm flipping. So I'm flipping this fraction now. So I'm going to go ahead and factor the denominator and put that in the numerator. So that's going to be x plus 9x minus 1, I think. Yeah. And then I'm going to factor that denominator. I'm going to factor out an x, and then that's going to be x minus, is it x minus 9? X minus 9, and then an x, what multiplies into 27 adds into negative 6. 3, right? It would be a positive 3. Okay, so then stuff's going to cancel now. I like to say create a super fraction here when it's multiplication, right? You can actually just extend that fraction bar on out, and we can just do some cancellation now. So the x plus 9's cancel, the x minus 2's cancel. And I think you're left with this. You are left with an x plus, or an x minus 1 all over x times x minus 9 times an x plus 3. I think, what is that, 15b? Yeah, that looks good to me. All right, looking at C, so adding and subtracting fractions is actually harder than multiplying and dividing, right? Because if I had, like, say, for example, 1/2 plus 1/2, that would not be 1 plus 1 is 2, and 2 plus 2 is 4, which reduces to 1/2. Gotcha, math. No, right? You would, once the denominators are the same, add across the top. 1/2 plus 1/2 is intuitively 1. 1 plus 1 is, so this is wrong, 2 over 2, which is 1. So we need like denominators, then add across the top. As of right now, these are not like denominators. So I need to make them like denominators by finding a least common denominator, an LCD. Right, if I had like 1/3 plus 1/2, the LCD would be 6. I can multiply the left one by 2 over 2 and the right one by 3 over 3 to get, what is that, like 2 over 6 plus 3 over 6 to get 5/6, right? Anyway, so I'm going to go ahead and factor the denominator. That's going to help me do exactly what I'm setting up for on the right side there. This is going to be x plus 2 times x minus 1. And then this is plus 1 over x plus 2. So notice here how the left denominator has a factor of an x plus 2, but it has an additional factor of an x minus 1. We need to multiply this right fraction by that additional factor over itself. X minus 1 over x minus 1. So then this would be x over, well, the same thing. I'm literally just rewriting this expression. And then it'll be plus the x minus 1 all over, hey, look at that, like denominators. So now I can add across the top. Final answer is going to be 2x minus 1 all over the x plus 2 times the x minus 1. Okay, last one here. I'm going to factor that denominator, so it's subtraction. For subtraction, you can just do this, watch. So I'm going to factor the denominator to x plus 3, x minus 3, difference of two squares. You can think of this as like plus a negative 3, right? Like if you're adding a negative, that's the same as subtracting whatever that number originally was. And then this is already factored for you down below. That was nice. So it's x times x minus 3. Okay, so it looks like the right side is missing an x plus 3 for the LCD. And the left side is missing just an x for the LCD. So now we have the same denominators, x times x minus 3 times x plus 3. So that'll be an x squared over what I just said, because I don't want to keep saying it. And then I'm going to distribute this negative 3 to both terms. So it'd be a negative 3x minus a 9. And then it's over that x times x minus 3 times x plus 3. Okay, we got like denominators, people. So up in the numerator, what's going on? X squared plus, nope. That is a minus 3x. So x squared minus a 3x minus a 9 all over the x times x plus 3 times the x minus 3. Done with adding, subtracting, multiplying, and dividing rational expressions. So like, by the way, as we're going through this, like real casually, 15 alone, I don't know how long it just took me to do those 4 problems, is like a week in like an Algebra 2 course. And we you know, this is a long video, I'm sure, but I just did a week worth of content in 4 minutes. So you're getting your value here, I'm thinking. So if you're still with me, hey, you're awesome and you're committed. So like, commit to the grind. You're with me right now. Like, I think you're past the sunk cost fallacy moment, and there is no sunk cost. Like, it's gonna be worth it. But you're past that little moment because we're right around like the 30-something% threshold. I don't know the psychology behind that. Okay. Well, all right. Psychology aside, we're doing math. We're solving rational equations now, or like maybe a third of the way through. A little more. Solve the following rational equations below. Okay, so if you have a fraction equal to a fraction, you can in fact cross multiply. But remember, cross multiplication isn't this like fancy operation. It's really just doing LCD stuff. So like, sure, and sometimes kids say like butterfly method. I don't know what the heck that is. The only butterfly I know is the one that's starting. Is it tsunamis or hurricanes? Butterfly effect, right? So anyway, you can cross multiply here, and then you can just set this up as x times x plus 7 is equal to, well, what's going to be 3 times a negative 2. But I just want to show you what you're technically doing is LCD stuff. You're multiplying the right side by what the left side has, right? 3 over 3, and then you're multiplying the left side by what the right side has, x plus 7 over x plus 7. So you're getting x times x plus 7 all over. I gotta show this, people. Like, if you don't know what cross multiplication secretly is, then it's gonna irk me. So what is that? Negative 6 over the 3 times the quantity of x plus 7. And then since you have the like denominators, you can just add, set the tops equal to each other, which is the same thing as this. So cross multiplication just skips this little middle step. You're technically doing LCD stuff. Anyway, distributing that x in, you get x squared plus 7x, and then this is equal to a negative 6. So x squared plus 7x plus 6 is equal to 0. This does factor to x plus 6 and x plus 1. So final answers are negative 1 and negative 6. Okay, next one. Not as easy as the cross multiplication scenario, but it's also not that bad. Instead of multiplying in a way where you're getting all the like denominators, you're actually just multiplying this whole equation by what the LCD is instead, and actually that makes the problem a whole lot easier. So we notice that this x squared minus 9 is a difference of two squares. That's x plus 3 times x minus 3. So really that's what we're going to be multiplying both sides by. X plus 3 times x minus 3. Check it out. If I distribute this to all like 3 terms kind of within the rightmost one, the x plus 3 cancels with the x plus 3, and the x minus 3 cancels with the x minus 3, so you're just left with 2x plus 2. Life's good. Within the first one, the x minus 3's cancel, but the x plus 3 is still there, so that'd be 4 times the x plus 3. And then within the second one, the x plus 3's cancel, but the x minus 3's are still there. So I'm going to make it look a little prettier. We're left with this linear equation. Life's good. Linear equations are an easy game at this point. So this is 4x plus 12, and then plus 2x minus 6 is equal to 2x plus 2. Combine like terms, we get 6x plus 6 is equal to 2x plus 2. That would be 4x is equal to negative 4, so x is equal to negative 1. Good. All right, next on the agenda is polynomial long division. That's a fun one. So there's like a day you have to do polynomial long division in Calc 1, not even in Calc 2 or 3. And I'm going to just show it because it's a thing. And yeah, it's found in an earlier course. But this is not that. I would say everything on this page so far, the rational expressions, they're useful, but not so much polynomial long division. You won't do this too often, but you will do it. So at least in Calc AB. So I'm doing this. I'm writing my divisor on the outside. I'm like setting up for something like this. So if I have like, if I had like 700 over 5, I can write that as 5 is the divisor and 700 as the dividend. So I'm doing the same thing here. The 2x minus 1 is the divisor, and then the 4x cubed minus 2x squared plus 6x minus 7 is the dividend. And the way we do this, we actually just look at the leading coefficients. They lead the charge. And we think to ourselves, what do I have to multiply 2x by to get to 4x cubed? Well, 2 times 2 is 4, so I know it's going to be at least a 2. And then x times x squared is x cubed, so it's a 2x squared. And then what I'm subtracting off from the dividend is 2x squared times the 2x minus 1. So that would be the 4x cubed, which you always want a match of the leading coefficients as you subtract. That's the point. And then minus a 2x squared. And as you subtract this going down, you'll always get this cancellation effect here. So negative 2x squared minus a negative 2x squared. This isn't always going to happen, by the way. This was a nice thing that happened here. These do also cancel. Negative 2, yeah, they do. So you're just left with what remains? 6x minus 7. Okay, and then what do you have to multiply 2x by to get a 6x? Well, that's just a 3. So I'm going to be subtracting off 3 times this 2x minus 1. So it'll be 6x minus, was that 3? Right? So the 6x's cancel here, and then you're left with negative 7 plus 3, so that's a negative 4. So that's your remainder. So the way we write the remainder is we just add it as negative 4, but we're still dividing it by the 2x minus 1. It just, we can't divide it because it's 2x minus 1 is too large of a degree. So that would be our remainder. Still left to be divided by the divisor. Okay, looking at the next one, we got this x minus 4 on the outside, and we are dividing out this x to the 4th minus 3x cubed minus 6x squared plus 32. Looks good to me. So I want to do, okay, what do I have to multiply this x by to get to the x to the 4th? That would be x cubed. And then I'm subtracting off that x to the 4th minus 4x cubed. And you're getting that cancellation of the first 2 terms. If we keep the party going, we got negative 3x squared and then plus 4x cubed. So that would be x cubed, and then everything else just kind of drops down, just like how these drop down over here. So it's a minus 6x squared plus 32. Okay, what do I have to multiply this x by to get an x cubed? Well, that's just an x squared now. So I'm going to be subtracting off x cubed minus 4x squared. And then we get that cancellation, and we're left with negative 6x squared plus 4x squared. So it's a negative 2x squared plus 32. All right, and then we're trying to see what multiplies, what do we have to multiply this x by to get to a negative 2x squared? Well, it'd be a minus 2x at this point. And I'm going to have to continue this on this dead space over here. So negative 2x squared plus 32. I'm subtracting off a negative 2x squared. I'm multiplying this negative 2x by this minus 4. So this would be plus 8x. Cancels. Good to see. And then you're left with negative 8x plus 32. We're almost there. What do I have to multiply x by in order to get to a negative 8x? It would be a minus 8. And I'm subtracting off a negative 8x, and then negative 8 times negative 4 is a positive 32. And look at that. The negative 8x's cancels and the 32's cancel to leave us with a remainder of 0. So final answer is just that x cubed plus x squared minus 2x minus 8. So this division worked out nicely, where we had no remainder left. Okay, all right. We pushed through. Okay, we got finding vertical asymptotes, horizontal asymptotes, and holes. So if you just have a normal rational expression like 1 over x minus 2, this is just the parent rational expression, 1 over x shifted 2 units to the right. You can find the asymptotes by setting the denominator equal to 0. That's how you can find the vertical asymptotes. So we have a vertical asymptote at x is equal to 2. Horizontal asymptotes, you look at the degrees of your numerator and denominator. If your degree is larger down below, your horizontal asymptote is y is equal to 0. If they're the same degrees, you take the leading coefficients. And if the degree is larger up top, there is no horizontal asymptote. So here, the degree is larger down below. You have an x to the first and constant up top. So you have a horizontal asymptote at y is equal to 0. There are no holes in this. Holes occur when when you have like a cancellation of the same two terms. You'll see pretty much like right now. Okay, so I'm going to do that. So looking at this next expression, I'm going to factor that denominator because I'm going to have to anyway to find my vertical asymptotes. I'm going to be left with x minus a 2 and then plus x times x plus a 3. Right? That would be the correct factorization. Good. So you'll notice that these would end up canceling. Kinda. Sorta. Okay, so here's the thing. This is pretty much 1, right? If you plug in any number for x, you're going to get 1. The issue is the number 2. Because if you have 2 minus 2 over 2 minus 2, that's 0 over 0, which is not 1. That's an indeterminate. So what we actually end up getting there graphically is a hole in our graph. I'll show this on Desmos. So what you get is vertical asymptote at, well, you would set that x plus 3 equal to 0. So it'd be at x is equal to negative 3. You have a horizontal asymptote still at y is equal to 0. Because the power is larger down below. But then you have a hole at x is equal to 2. And this has to be shown, right? Let's show it. Let's show it. So you have this x minus 2. Ooh, I didn't see that plus 1 there. I'm gonna explain that in a moment. And then it's x squared plus x. And then minus 6. So what that plus 1 does is, yoink, it just shifts it up 1 unit. So I'll just kind of go back and forth between those two. Do you see how it kind of just scoots up? There, that's a bigger picture. Plus 1, plus 0. Plus 1, plus 0. So that will change our horizontal asymptote. It'll just nudge it up by 1. But in terms of what the hole looks like, you'll see a vertical asymptote at x is equal to negative 3. This line right here, there's your asymptote. And then at x is equal to 2, I don't see a hole. What if you just zoom in like a whole lot? I don't see it. But what Desmos does, which is really nice, is that if you hover over it, you'll see that it's actually undefined. At that value, there's your hole. Okay. keeping this moving. We can factor the top here for this next one to be x plus 2, x minus 2. And then down below, I think you can factor out a 2, right? Yeah, factor out that 2, and then we would be left with what multiplies into negative 2 adds into 1. That would be x plus 2, x minus 1. Okay, so looks like we got a hole at negative 2. Yes, let's go through this. We got a hole at x is equal to negative 2, because the x plus 2 is canceled, right? And then let's see, the horizontal, let's do vertical asymptote. Vertical asymptote is going to be at, well, you just set this x minus 1 equal to 0, so that's at 1. And then the horizontal asymptote, well, wait a minute. The powers were matching. We have an x squared over 2x squared. So you're just taking the leading coefficients. What's in front of this x squared is a 1, so we have a horizontal asymptote at 1 over 2. The idea behind a horizontal asymptote is what were to happen if we were to run toward infinity. So just plug in a really big number. If you were to plug in a really big number, this minus 4 wouldn't really do much. This minus 4 really wouldn't do much. Even this 2 times infinity really wouldn't do that much, because you have 2 times infinity times infinity. It's like when you're at like a, I don't know, childhood playground, 2 kids kind of just saying, well, I have infinity money. And no one does, but I have infinity times infinity money. I was like, whoa, that's way bigger. It actually is. But remember, infinity is a concept, not a number, so it gets a little fishy there. That's why we have calculus. So vertical asymptotes at 1, horizontal asymptotes at 1/2, and holes at negative 2. Okay, for the next one here, we have a higher power up in the numerator, so that means that you have no... This is not a funny rational expression. No ha's. No horizontal asymptotes. The vertical asymptote does exist. It happens at... Now wait, we got to check to see if this is a hole though. It's not funny, and it's not even funny to vampires. You'll get that in a second. Or you got it right now. Because I can factor this numerator to x plus 4 and x plus 5, and then the x plus 5's canceled, right? So there's no vertical asymptotes either. Okay, so that's actually a hole. So we have a hole at x is equal to negative 5. This is a fun expression to graph. I'm having a blast right now. I'm only on hour 2 of this. Actually, it's not that bad. But we got a ways to go. So I got x squared plus 9x. This might be my last day of summer too. This is the way to leave summer in a bang, by doing math. All right, so at negative 5, we'll see. So this looks like just a line, right? Innocent, right? But not innocent at all, actually. You little liar. You got this hole right here. I see you for what you're worth. And it's a lot, because we all have worth. I've been trying to be wholesome at the same time. Man! I'm full of this. Chock full of it. This is what happens when you lose your mind doing mathematics. Okay. For the last little section here, these aren't terribly important, but they can happen where you have to deal with like an interval that might be a rational interval, and yeah, I'm just going to do the problems here. So it's the same exact number line trick. Same exact number line trick, except you have to also include the asymptote. So, you know, where the 0 is going to be at. Well, you can get a 0 at 1. You can get a 0 at 3. But remember, something weird happens at 5. You get an asymptotic behavior, and you need to see if this asymptote is kind of like a volcano asymptote, or if it's like a goes down here, up here kind of asymptote, or maybe it's like a downward pointing. You know, there's a lot of different variations of how the asymptote may behave. So actually there's 4, not a lot, it's only 4. So we have to kind of like test around the asymptote as well. So I'm going to go ahead and plug in like 0. If I plug in 0, that would be a negative times a negative over a negative, which is a negative, right? Yeah, it is. if I plug in 2, that would be a positive times a negative times a negative. So the negatives would cancel, so that'd be a positive. If I plug in like a 4, that's one between them, right? That would be positive times a positive over a negative, so it's a negative again. If I plug in like 6, positive, positive over positive. So it looks something like that. So when are we less than or equal to 0? Well, it's going to be from 1 inclusive, because it's an or equal to 3 inclusive. And then union, we don't want to include 5 because 5 doesn't exist on the graph in the first place. That was our asymptote, right? So parentheses on that 5 and then up to infinity. So we include the 1 and the 3 because the 1 and the 3 exist on the curve. Those are just when they cross through the x-axis. I'll show this graph. And then the 5 we don't include because that is the vertical asymptote. He will show x minus 1, x minus 3 all over x minus 5. All right, so when are we below the x? Oh, I just gave, I gave the when we're above. Okay, so this would be if this was a greater than or equal to, but it's a less than because the alligator says so, right? I don't know if you guys were taught this way. That is, I did not make that look like an alligator, but yeah, it looks like the alligator is eating the bigger object, right? That's like the middle school way of doing it. Anyway, it should be corrected to when these are negative. So it'd be from negative infinity to 1 inclusive, union, inclusive on 3, 5, and then parentheses because 5 is an asymptote. Okay, and then we're going to prove this graphically. So you can see here, okay, so for negative infinity, all the way up to, bam, 1, we're below the x-axis, and then we're above it from 1 to 3. And then at 3, we go below it again. And then we don't include 5 because it kind of doesn't exist, or it just strictly doesn't exist. And like right when you get to like 5.000001, you're all the way up here, and then you're up for the rest of your journey. So you have 2 intervals, 2 little sections. Alligator eats the bigger number in inequalities. Okay, the last few here. We got what would happen if you have a multiplicity of 2. Actually, we can just use the same number line, right? For all these. That was kind of the point, right? I forgot I did that. So not a lot more needs to be done. We can actually just use that multiplicity 2 idea to our advantage. Because you'll notice this has multiplicity 2 around the 1. This has a multiplicity of 2 around the 3. And then you get that similar effect for part D. You'll see. All right, so it started off, if I were to plug in a 0, this would be a positive, this would be a negative, and this would be a negative. So this would be a positive right here. And then it's multiplicity 2 there, and then the rest kind of just behaves as normal. It just kind of alternates. So if I'm considering when I'm less than 0, it would be from just 3 to 5, it looks like. Remember that when you don't have the or equal to, we're just including everything that's on the inside, not at the endpoints. For part C, I'm going to plug in like 0 again. It's an easy number to plug in. I'm going to be left with a negative times a positive, and then this is all over a negative. So negative over negative makes a positive. So this would be a positive output here. And then once we get to like 2, this would be positive, and then, well, we just get the normal alternating behavior. It's the 3 where we get that multiplicity 2 effect. So it'd be a minus and then a minus there. And then the alternating pattern kind of continues. And you can plug in numbers to test this if you kind of don't feel right taking that shortcut. Anyway, we're trying to figure out when we're greater than 0. So this will be from negative infinity to 1, non-inclusive on the 1 because we don't have the or equal to, and then union 5, which is an asymptote, which we're not going to include anyway, to infinity. And we can never include infinity as well. Okay, and then the last one for rational expressions. So just go through the normal business. I'm going to plug in 0. It'd be a negative times a negative over a positive. So that's a positive, and then a negative, and then a positive. But then remember, 5 has this multiplicity of 2 effect, so then a positive again. Okay. So when are we greater than or equal to 0? This one's a little funky. So it'll be from negative infinity to 1, and then union. Well, I want to include the 3, and then I go to 5, but then I stop at 5 because it doesn't exist on 5. So I use a parenthesis, union, and then I resume on 5. This isn't sus, it's an asymptote. And we're skipping over it. So I don't include it on either end, and then I just run towards infinity forever after. Oh, parenthesis there as well. Feel free to graph these if you want to verify them. I'm done with rational expressions. Moving on to exponents. On to part 5. Exponents aren't too bad, but they're pretty essential for the class, so we see them pretty often. Oh, we got a visitor, everyone. Come on in. Yeah. All right, Lucky will be joining us for some of the exponents. All right. So Lucky remembers that when we are multiplying two bases, we are adding the exponents, right? This is the same thing as x, because there's two x's here, x times x times x times x times x, right? So there are 5 x's in total, x to the 5th. And what we just added the exponents. Here, this is the same thing as, well, I have 3 of these x squareds. So x squared times x squared times x squared. Which is x times x times x times x times x times x. So that's x to the 6th, and what we did was we multiplied the exponents. And we already saw this one in the rational expression section. This is just x times x all over x times x, which is, you get the cancellation here, just x. Right, Lucky? Okay. She'll stay here as long as she wants. She might leave right away. She's like, wait a minute, we're doing math? I'm out. Okay, something that I see frequently. I think students generally know that if you have a negative exponent, you bring it down to the denominator, but they get confused when it's attached to like a coefficient. This coefficient, this 4, is just raised to the 1st power. This does not drop down alongside the this x to the 3rd. So this is going to be x times that 4, the x squared, sorry, times that 4, and then just the x to the 3rd is going to make its way down to the denominator. X squared over x to the 3rd, that's just going to be 4 over x. So final answer. Whereas here, this 4 is also captured inside of the negative 2 exponent. So this is going to make its way down, this 4. So this whole expression is going to make its way down to the denominator. It's going to be quantity of 4x cubed all to the 2nd now. And then you can think about that as 4x cubed times 4x cubed. I think she's thinking, she's had enough of this. Well, let's just finish this example. Is that okay? She says that's okay. So this is going to be 1 over, what is this? So 4 squared, so it's going to be 16 times x to the 6th. Right, this is the same thing as 4x to the 3rd times 4x to the 3rd. Okay. Lucky, you've had a great time doing some math with me. Okay. For the next one, we're looking at a negative exponent down in the denominator. We can just bring that on up to get x squared times x to the 3rd all over just a 4 now. So that 4 is not raised to that exponent. And then now we're just looking at x to the, it's a multiplication, x to the 5th all over x. No x's, just a 4. All right, next one. Rewrite the following expressions using rational exponents. Okay, we just did the big 3, I would say, over here, right? Exponent rules that you did like back in like an Algebra 1 course. Now we have rational exponents, which is more Algebra 2 style. So with these, we can rewrite, say, the cube root of x as x to the 1/3, and we can rewrite the square root of x as x to the 1/2. And then the normal rules apply. So 1/3 plus 1/2, I think we did that earlier. 1/3 plus 1/2, that would be, multiplying this one by 2/2 and this one by 3/3, right? We end up getting 5/6. Okay. Next one, B. We got an addition between them. So sure, you can rewrite this as x to the 1/3 plus x to the 1/2, but you can't do anything else. The whole problem's done. And the reason why is because of addition. It's only through multiplication and division that you can do, get addition of the exponents or subtraction of the exponents. Here, addition between the two, can't do a thing. Here you kind of can, because if you got one of these things and then another one of these things, you got two of these things, right? But that's all you can really do. The 2 is just sitting up front, and then you have x to the 1/3 off to the side. Over here, so if your your square root of x is down in the denominator, that's like bringing it up to the numerator and then also writing it as, x to the 1/2, right? Because that would be the same thing as the square root of x, so it would be x to the negative 1/2. And then plus, so it's saying, just using rational exponents, so this would be x to the negative 2/3. So the index is your denominator. That's what's on the outside of the radical. And then your power is on the inside, which is your numerator. Okay, we got, so on the same note of that, this one would be x to the 2/3. And then this one, there's kind of like a hidden 2 here with the squares. That's kind of how we think about it. X to the 3/2 for the second. Now, anything you do here because addition, don't touch it. You can't do anything with that. And then for our last situation here, we have the square root of x to the 6th. Nope, don't do the thing that you were just teaching earlier. X to the 5th, right? Because there's 2 of them here and 3 of them here. So there's 5 of them in total. It would be if you had x squared. If you had this case, it's x to the 6th. So this would just be x to the 5/2. So eventually you'll have to do what's called integration, and having rational exponents is very useful for that. Okay, moving along. 22. We're actually doing great. There's only 50 problems. Not that bad. So almost halfway there. Write each expression below in radical form and with positive exponents. Okay, so this would be the same thing as 1 over x to the 2/3, which is the same thing as 1 over the cube root of x to the 2nd. Over here, this plus is, you should be cautious of pluses now, right? If you have that 1/2 up front, you have the square root of x squared plus 4. Do not, in either of these situations, distribute the square, because that kills a cat. Never, never a dog. Oh, she has left. I thought she was just going to be right behind me. Don't break Aunt Sally's demands. I don't know if they're demands, requests. We can't distribute this power in the same spirit as why we couldn't distribute it in the case where you had like a binomial squared. It's the same idea. Why you can't. Anyway, leave as is. All right, so looking at C, we can rewrite this as x to the 1/3 over x to the 2nd. And then we can rewrite this one as 1 over x to the 2/3, right? Because negative 2 times 1/3 is negative 2/3, and then bring that down in the denominator. We can subtract now for the exponents for the first term. So that would be like x. So 1/3 minus 2 is x to the, it'd be to the negative 5/6. No, 5/3. Yeah, so that would be brought down to the denominator. So it'd be 1 over x to the 5/3 plus 1 over x to the 2/3. Something like that, right? 2 minus, you can also do it the other way, right? From denominator to numerator, 2 minus 1/3 is 5/3. 6/3 minus 1/3 is 5/3. Okay, oh, it's saying write them as radicals, so I didn't finish that. This would be 1 over the cube root of x to the 5th, and this would be plus 1 over the cube root of x to the 2nd. You can't do anything because there's a plus in between, right? Okay, for D, this would be the same thing as 8 cube root of x to the 2nd. That 8 is on the outside of the 2/3, right? Whereas with E, the 8 is on the inside of the 2/3. So this is the same thing as 8 to the 2/3. times x to the 2/3. And 8 to the 2/3 is a thing that we can compute. You can either do 8 squared first and then the cube root of that. So 8 squared is 64, and the cube root of 64 is 4. Or you can do the cube root of 8 and then square it. So the cube root of 8 is 2, and then 2 squared is 4. So this would be 4, and then times the cube root of x squared. And then for the last one, this is just going to be the square root of 8 plus x all cubed. You can put a 2 there if you want to, but you don't have to. In fact, it's kind of weird if you do that, so don't do that. But it's implied within the square root. All right, done with that. Last little section here. Simplify each given numeric expression below completely. So this is just playing around with the idea that we just saw right here. So numerically, what we're about to do is not a whole lot. They're going to be written, expressed differently, the numbers I write for each of these, but numerically they're going to be the same value. So for example, I can split root 98 into a number times a perfect square. So know your perfect square numbers. That's 4, 9, 16, 25, 36, 49, 64, 81, and 100, so on and so forth. So here you can split this into root 49 and root 2. The square root of 49 is 7, so that's just 7 root 2. So and this is teacher discretion. So some teachers would just take root 98 as a final answer, and then some wouldn't. Same thing with rationalizing. I realized I did not do rationalizing any denominators here. So like if I had 1 over root 2, you would rationalize this to be root 2. You'd multiply by root 2 over root 2. The reason why is root 2 times root 2 is just 2, right? You can even think about it this way using exponent laws, right? 2 to the 1/2 times 2 to the 1/2, that would be 2 to the 1st, right? 1/2 plus 1/2, same bases. Anyway, so this would be root 2 over 2. So these are equivalent, right? That's all I'm trying to say, is that 1 over root 2 is the same as root 2 over 2. That's called rationalizing the denominator. So this is teacher discretion. Some teachers are going to say, hey, you got to do this. Some, it might be like in the multiple choice setting, you would have to just be, be keen enough at, I mean, it's numeric literacy, kind of be good enough with numbers to see that they're the same. And I'm just giving you the tools there. Okay, so for cube root of 125, what times what is 125? That would be just 5. Sometimes you can simplify it, sometimes you cannot. So for the 4th root of 32, what times what is 32? It's not 2, because 2 times 2 times 2 times 2 is 16. It's not 3, because 3 times 3 times 3 times 3 is 81. So it's got to be between 2 and 3. So what we do is we create a factor tree when it's not factorable. I could have done a factor tree here, 98. That you can split this into 49 and 2, and then 7 and 7. And then you would like circle your pairs for power of 2. Where here I'm going to do something similar. I'm going to split up 32 into, I don't know, 16 times 2, split that into 8 times 2, split that into 4 times 2, and split this into 2 times 2. And then you would kind of like circle or pair up all your, in groups of 4 for this one, where for A it was in groups of 2, because it's a square root. Here it's groups of 4, because it's a 4th root. So all these 2's together make it on the outside, just like how this 7 made it on the outside. And then one of these 2's are trapped, still underneath the radical. So it'd be 2 4th root 2, which is between 2 and 3, probably. Yeah. Anyway, for D, I have a choice. I can either square this first or cube root it first. I'm definitely going to choose the cube root first. Cube root of 64 is 4. So it'd be 4 squared, and 4 squared is just 16. Life's good. And then over here, same story. I can either cube the 64, the 16 first, or I can square root it. I'm going to square root it. That seems a lot faster. So I'm going to get 4 to the 3rd, and 4 to the 3rd is that 64. So these are all numerically equivalent. The AP exam doesn't, at least as of this year, in years prior, many years prior, if it's numerically equivalent on the free response, it'll just take it. That's how I teach too. So yeah, teacher discretion. Okay, so what are some important mini lessons here with radicals? Okay, it's tempting to say these just kind of cancel, and they sort of kind of do. But consider like a negative. if I were to plug in like a -3 here, okay, so -3 squared is a positive 9, and the square root of 9 is just 3. So hold the phone. If I were to plug in a -3 into this machine and a positive 3 shoots out, what type of function out there allows us to plug in a negative and then the positive version of it shoots out? This is actually the definition of the absolute value of x. So that might be useful, depending on what kind of class you take, version of calc you take. It's useful in AP Calc. And then over here, so don't distribute the square root. Don't do that. Don't do that at all, especially this expression. This expression is just the top half of a circle. So x squared plus y squared is equal to 1 is the unit circle. If I move this x squared onto the other side, I get y squared is equal to 1 minus x squared, and I take that square root. The plus or minus would be what I need in order to create the full circle. But if you have just the positive version of it, that would be the top half of a circle. The negative is the bottom half of a circle. Here, it's actually kind of satisfying to show that one. So I'm going to do that. So we know that the circle is x squared plus y squared is equal to 1. Zoom in a little bit, right? When we do the y is equal to the square root of 1 minus x squared, that's just the top half. So I can turn this off temporarily. And of course, if I do the negative version of it, that would be the bottom half. So together, they make the full circle. All right, and then, so there's really not a lot going on here. Just like, this is a semicircle. You should look at this and just be able to tell it's a semicircle on inspection. That's a useful skill in the class. Okay, what else is useful? So knowing the difference between just the square root of 9 and then solving the equation x squared is equal to 9. These are different things. Something that kind of bugs me is I listen to a lot of Star Talk with Neil deGrasse Tyson, who's awesome, a great physics educator, but he sometimes gets this messed up. So, all right, in the context of solving, you would get a plus or minus 3. And there are two solutions that work for this equation, a positive 3 and a negative 3. But a square root by itself, just square root 9 by itself, is just 3. It is through the context of finding the inverse of a square that both 3 and negative 3 work for the equation, the quadratic equation x squared is equal to 9, and you get the plus or minus. There is no plus or minus if the root 9 is just by itself, right? If like over here, you know, I didn't do a plus or minus in front of this expression because it wasn't through the context of solving. Where if it was x squared is equal to 98 and I took the square root, then it would be plus or minus 7 root 2. Minor thing. Okay, and then lastly, on the notion of plus or minuses, because that has come up quite a bit, the sign. So, I mean, really, what's like 30% of calculus errors, like sign related. Would I say 20%? I think 20% maybe, 10 to 20%. Not 80, but a lot. Okay, so I'm going to take the cube root. It says to solve for y. I'm going to take the cube root of both sides here. Here, everything's good. You get y is equal to the cube root of x. No issues. But when you take the square root, remember the square root spawns a plus or minus. So this equation actually creates two equations. When you solve for y, you're going to get y is equal to the positive square root, but then you have the plus or minus. And also kind of like and, you get y is equal to the negative square root of x. So this I also want to show right here. So if I consider the sideways parabola x is equal to y squared. If I were to just take the square root of both sides here, I would get y is equal to square root of x. So we see the same idea in play as we just saw with the semicircle, but you need the plus or minus because it's an even power. So I guess I'm just graphing all of it for this one for some reason. Square root, squirt x, and together they make up the full original image. Yeah, there it is. Okay, so for even powers, you don't have to worry about the plus or minus, or you do have to worry about the plus or minus, and then for odd, you don't. Okay, done with radicals. Gnarly. Awesome. Moving on. The basics of functions. A lot of these are Algebra 1 base skills to the beginning, and then some Algebra 2 or advanced algebra skills come into play in the second half. All right, so function inputs and function outputs, you got to know this through an equation, a function, a table, or a graph. So in goes a number, out shoots a number. That's how functions work. Remember, functions are, you cannot have a single input with two outputs. But an output can be repeated. So like the best example or analogy to that is that if I walk to a store and I buy some items and it comes out to exactly $20, it is possible that I can buy some other group of items and it still comes out to $20. So like that 20 can be repeated, but not one object having two different prices at the same time. That is not possible. So that would break the idea of what a function is. For every input, there's just one output. Okay, but the outputs can repeat. Anyway, like you can see here with the parabola, so like here the 4's repeat. Okay. Anyway, for real, let's do the questions. Okay. So looking at the first one, the input's 1, so I'm just plugging in 1. So this is 2 times 1 plus 4. This is just 7. Over here, it's saying a thing. It's saying if f of x is equal to 12. What would x have to be equal to? So I'm just setting 12 equal to 2x plus 4. And then I'm solving for x. So I'm going to be moving that 4 on over, dividing by 2. So that would be 8 is equal to 2x, so x would be equal to 4. So 1 is an input here, and then 12 is the output, right? So two different problems. All right, so for the next one, off a table, very straightforward. F of 1 is just 10. And then if your output's 15, x would be 2. So tables are pretty good. Looking at graphs are fine too. So if now the scale of this graph is a little wonky, just so you know. So f of 1 would be equal to 1 here, right? This is the ordered pair 1, 1. So when you have an input of 1, you have an output of 1. And then at 8, so if you have an output of 8, so this is 5, 6, 7, 8. The output is 8, so the input is 2. This is 2, 8. So the x value would be 2. Okay, nothing too crazy, but you do need to be kind of proficient at, I don't know, this part of functiony stuff. Okay, looking at domain. So if you have a discrete data set for a function, it's rare, but can technically happen. Remember, this is just a way to introduce domain. Domain is your set of x. So the x values here are 1, 3, and 5. You won't really be dealing with discrete functions in calc, but domain is x and range is y. That's the takeaway here. So the range are the even numbers, the 2, the 4, and the 6. So done with that. What you're really going to be dealing with are like algebraic functions and then curves. The curves, I mean, that's the point of calculus, is the study of the infinite with curves in particular. But anyway, so more of what we really are going to be looking at. The domain here, and we're going to be listing them in interval notation because they're continuous and they're not discrete, which are just like data points. The domain here, we know what the parabola looks like. The parabola just looks like this. So every x value is attained from left to right. So that would be negative infinity to infinity. However, the range, you'll notice that we don't hit anything in this bottom space down here. The parabola just is from 0 to infinity upward. So we would say, well, inclusive 0, because we do hit 0 at 0, right? The origin 0, 0, and then up to infinity. Whereas for, here's the rational parent function. So we have this looking thing. So we'll talk about parent functions obviously shortly. It's the next little thing, but you should know the parent functions. Anyway, it looks like this, 1 over x. It's in the first and third quadrant. And it has the asymptotes, right? It has an asymptote, horizontal asymptote at y is equal to 0 and a vertical asymptote at x is equal to 0. So with that said, we're skipping the zeros. So we were going to go for domain negative infinity to 0. There's an asymptote, so skip it. And then from 0 to infinity. And actually the same thing happens for the range. From negative infinity, so from bottom to top, we skip 0. And then we hit everything above it. So from negative infinity to 0, union 0 to infinity. So we have these things called discontinuities. So continuity is important for calculus, like if your curve is continuous. And a curve is not continuous when it experiences what's called an an infinite discontinuity. Yeah, there we go, for asymptotes. And then there's two other discontinuity types. A hole, which we've already seen, and then what is called a jump discontinuity, which, hey, down here. So when you see your function kind of just like doing its thing, cruising, hanging out, and then whoop, and all of a sudden it just teleports. So you have jump discontinuities, infinite discontinuities, and holes, which are called removable discontinuities. Those are all very important right away, Unit 1 of any calculus course. Okay, for D, you'll notice here that we have a closed endpoint and an open endpoint. So sometimes your function may be artificially stopped. So this is just some, actually here's the full function in part E, but we've kind of stopped it at our, these little moments for part D. So for the domain, this would be from non-inclusive on the -1 because it's an open circle to 2, and that would be a bracket because it's a closed circle. And then for range, now it's the y value. So this ordered pair would have been -1, 0. So the output here, y value, is 0, and we're not including it because it's an open circle. Likewise, this is 2, 6, so we're going to be taking the 6 from the right endpoint here, and that's the y value at that moment. So this could happen too, where it doesn't go on forever. It doesn't go on. You actually have an infinite number of points between these two finite values, which is kind of weird, which is why we need calculus too. But the interval itself is, restrained and confined to those strict values. Okay, looking at E. So this goes on forever, though. It's assumed that if it kind of goes towards the graph like this, usually it's kind for the writer to put arrows to indicate that this keeps going. But here I didn't, sorry. So yeah, this just kind of goes on forever. So it looks like there's no restrictions too. We go forever down, we go forever up, we go forever right, we go forever left. So this would just be from -infinity to infinity, and then the range would just also be from -infinity to infinity. Okay, looking at F, we do have an endpoint here, and then this is an arrow going on forever. You can have the combination of both, so this just looks like a parabola. And it looks to me like it is starting, now it's tempting to say from 6 to infinity, but this ordered pair is not, it does not start at 6. This is a mistake that like my freshmen would make a lot. They'd be like, oh, 6, infinity, right? There's the 6. Okay, but the x value is 0, right? This ordered pair is 0, 6. So we're taking the x value here, and it is inclusive because it is a closed circle, and then it goes on forever, right? And then for the range, well, you would also not take the 6 here because we want to go from bottom to top now. So what's the lowest part of your curve to the highest part? Well, it's actually down here at the vertex. So the lowest y value that this attains, now let's be careful here, is it the 1 or is it the 2? Hey, you got it at home. Nice job. You said 2, right? Go ahead. You said 2, right? Because we're taking the y value. We're taking the y value, not the x value for range. So it'd be from 2, and we are including it because we do hit the vertex. And then it goes up forever. Even though it stops on the left side at 6, the right side keeps going on forever, so 2 to infinity. Feels a little weird. All right, so parent functions. The parent functions that you need to know. A parent function is just like a basic default function. So for example, y is equal to x is the parent linear function. Y is equal to x squared is the parent quadratic function. So just off the top of my head, you got to know what all these look like. Y is equal to x, y is equal to x squared, y is equal to x cubed. Square root of x is a parent. Cube root of x is a parent. Yeah, try finding your baby mama here. I don't know. That was weird. I should cut that out. I don't know why it's this. I think the idea parent is these are like you can perform shifts to the starting point. So like you start at your parents, I guess. So it's kind of an odd name. The more I think about it. What other parent functions do we have? We have absolute value of x. We have 1 over x. These are the ones we just did so far. But you have more parent functions. We're going to be doing some like precalculus functions shortly. So like you'll have like, there really isn't like an exponential parent function. I guess people say e to the x, and I'll talk about that a little later, or like natural log of x. Sine x, cosine x, and tangent x. Know what all of these look like. Yeah. Know what all of them look like. And if you're like, man, I don't know what these look like, graphing on Desmos, dude. All right, so 27. So we want to identify the parent function. So here the parent function would just be the square root of x. Because, you know, if you kind of remove the gunk, remove the 2, remove the 1, remove the 3, you're just left with square root of x. We can just do the parent functions real fast. If we look at the next one, the parent function is just x cubed. So just get rid of that coefficient, just normal x cubed. And then over here, this one's a little hard to see, but this parent function is 1 over x. Right? Remove the gunk, remove the 1, remove the 2, remove the 3. You have 1 over x. Okay. So now we're describing the transformation. So I'm going to do just like a little mini. This is a pretty important skill. So let's just take the parabola, okay, x squared, and we're going to take it in vertex form. So y is equal to a times x minus h squared, and then plus k. Okay, so in short, what do all these things do? So a parabola in vertex form is essentially a parabola where you can easily find all the shifts and transformations that occur to it from the parent. So for example, if I wanted to move this back to the parent function, I would make h equal to 0, I would make k equal to 0, and hey, look at that, that's just x squared. So my h is inside the parentheses, this shifts it right and left. My k is on the outside of the parentheses, it's up and down. And then a is stretch, so imagine that I'm taking it and I'm like tugging it at its ends, or it's a compress. So here, when I make that number smaller or closer to 0, smaller magnitude, I'm like pressing it down. You can also reflect across like the x-axis. So here, this is reflecting across the x-axis when you make it, you know, this expression positive or negative. And then you can also reflect over the x-axis, which I will show, or the y-axis, which I will show over here. Okay, so what are the major shifts that occurred within 27a? Well, let's see. You have a stretch by a factor of 2. Stretch by a factor of 2. This minus 1 on the inside, it's kind of like reading it from left to right. You're reading it 2 units or 1 unit slower. So like it's a little difficult to think about this, but I will show it. So if I have the square root of x compared to the square root of x minus 1, you would think the minus 1 would move it to the left because that's where the negatives are, but alas, it moves it to the right. And the way I like to think about this is as I read the square root of x like a book from left to right and compare it to square root of x minus 1 from left to right like a book, I see it 1 unit slower. So that's kind of how that minus 1 goes. But it feels weird because, you know, it's not getting it into the positive territory. So I just feel like I needed to talk about that a little bit because I almost always get students getting that messed up. Okay, so it'll be shift right by 1 unit and then up by 3. Almost everyone understands that plus 3. So, all right, and then let's see, this next one, this one's going to reflect over the x-axis because it's negative, just like how we kind of showed. It'll be compress by a factor of 2. So instead of stretch by 2, it's compressed by 2 because you're dividing by 2 instead of multiplying by 2. And then that's it, right? Yeah, that's it. So it just reflects and compresses, that's all. So I don't know. I don't know if you're in your head, you're kind of like, oh, okay, I know the x cubed looks like this, and I know it's reflecting across the x-axis, so it's gonna mirror itself over the x-axis, and then it compresses itself, so it's gonna widen out a little bit. So I should look like this, sorta. Compressed and flipped. Okay, last one. This one's kind of hard. So this is a stretch by a factor of 3, because that's up in the numerator. The minus 1's obvious. That's it's down 1, right? Down by 1. The 2 is not so obvious. Well, here it kind of is. So if you had a minus 1 on the inside of your parent function alongside the x, this would be right 1. So here it's a positive 2, so it's a left 2. Now you might be thinking though, what the heck is up with this negative here though? Yeah, that's the hard part. So let's think about it. If you make the whole function negative, it reflects over the x-axis. If you make just the x negative, it reflects over the y-axis. So this reflects over y-axis. That one's not as important. At that point, I would almost say you don't even really need to know your transformations to that extent. But I definitely I would want you to be kind of cool with A and B coming into the class. Just understanding H is left, right, K is up, down, and then A is stretch, compress with a reflect over x-axis. Those are the big ones. Okay, composition of functions. Composition of functions. So the idea is f of g of 2. You can put, I mean, really think about going back to the money example. Like if I have some money and I go to a store, in goes money, out shoots item. And then maybe I like sell that item. So like out shoots that item and then I buy a new item. So, and then I get my new item. So it's going through it's just going through multiple functions. So like g of 2, you guys can figure out g of 2, no problem. G of 2 is just, g of 2 is just 2 squared, which is 4. So this is just the same thing as f of 4. And then you just find f of 4. So you just do it again. So f of 4 here is 2 times 4 plus 3. So final answer would be 11. Okay, and then over here, same story. You just go inside of the f first and then the g second. So f of 2 would be, let's kind of just do it off to the side like I did before. So 2 times 2 plus 3, that's 7. So this would be the same thing as g of 7, which is 7 squared, so that's 49. So, you know, g of f of 2 produces something different than f of g of 2. This always happens unless they're inverse functions of one another or something like that. I don't know, my brain is not working as well right now. Who would have thought that, like, you probably shouldn't do math for, like, hours and hours? Okay, let's look at 28C. So, okay, sometimes you see it in this notation. Don't be afraid. This is just h of g of 2. It's the same thing. So g of 2, we already computed that, didn't we? G of 2 is 4, so h of 4, 4 over 2 is just 2. And then you could technically do a function and a function and a function. So this happens with a little rule called chain rule, and that happens pretty quickly within the course. Maybe the first month or so, maybe second month of Calc 1. Okay, so h of 2 is 1. So this would be f of g of 1. G of 1 is 1, because 1 squared is 1. So this would just be f of 1. And f of 1 is, well, you just plug in the 1 over here. So that's 2 plus 3, which is 5. Okay. Done with composition of functions. Next, we have inverse. So for inverse functions, you're trying to figure out what function would create symmetry across the line y is equal to x. Or you can think about it this way. What function is the exact opposite function as the one provided? So for example, right now this x is being multiplied by 2, and then you add a 4. Okay? Remember that order, actually. Multiply by 2, and then add by 4. So I want to do the exact opposite of those rules in the exact opposite order. The way we determine this is we replace f of x, well, first with y, and then we flip-flop the x's and y's. So this would be x is equal to 2y plus 4. And we solve for the new y. So I would move the 4 onto the left and divide by that 2. So I would get, for my new y, I'd get y is equal to x minus 4 all over 2. So we'd say f inverse of x is equal to x minus 4 all over 2. So instead of multiplying by 2 and adding by 4, we are now subtracting by 4 and dividing by 2. So it's the exact opposite in the exact opposite order. Okay, the inverse function of x cubed, we can actually just jump to the answer here. The inverse function of that is the cube root of x. So you can also just know what are inverse functions of one another, like cube root and cube, they're inverses of one another. You could sit here and do it this way if you wanted to. The last one, this is going to be x squared, but there's a caveat because it's an even power. Remember, so x cubed, and remember I also mentioned that symmetry component, so I'm gonna graph this. X cubed, not to the 34th, and the cube root of x, CB, they have perfect symmetry across that line y is equal to x. Oh, look at that, looks beautiful. But I can't quite do that with the square root. So you'll notice here, x squared, so it's a whole even and odd thing, and that's a pretty big lesson of the course. They're not true inverses of one another. If you want to find the inverse of the square root of x, it's just x squared, but when we're greater than or equal to 0, and then you get that perfect symmetry. So sure, it is x squared, but when x is greater than or equal to 0. So even powers, you got to worry about this stuff. Odds, you don't. All right, lastly, for piecewise functions, oh, look at that absolute value. So we know that this is the square root of x squared, but there's another definition for it. You could split it into pieces, so it'd be f of x is equal to, and then we just use these curly brackets to denote, okay, I'm gonna list a few different lines here. It looks to me like this line is negative x from negative infinity to 0. So when x is less than 0, we're negative x, but then we're positive x when x is greater than 0. Something worth noting, what's happening at exactly 0, well, they're both touching there. So you can include that 0 in either the top one or the bottom one, but you have to be careful, because if you technically include it on both, which I'll do here in red to say don't do this, you're kind of telling the reader that this isn't a function, because you just have to be careful with that, because now you're saying it exists on both lines, which is technically like a point on top of itself. You definitely got to be mindful of it with jumps. Let's be clear on that one. But it's also kind of, I like to be mindful of it here, because I just say, okay, look, when you're exactly 0, just follow the bottom line. If you included both on, say, something like a jump, you're trying to be two different values at the same time, and then you break the definition of a function. So actually, let's talk about that. So here, f of x is equal to. Now, silly me, I didn't actually tell the reader which one to include. I'll just do a closed circle here and an open circle here. That needs to be clear, like ahead of time. I don't know, whatever, it happens. So if we have this case, you cannot have closed and closed. You can have open, open, but you cannot have closed and closed, because then it would break the definition of a function. A single input would have two outputs, and that's not good. It looks like we're just a basic parabola, x squared, when x is less than or equal to 0, because I have a closed circle here. And then we're just a horizontal flat line. We're just 1, because 2 is up here. So 1 is half that. So we're just the line 1 from when x is greater than 0. And then for the last piecewise, we have to do a little bit of work on this one. This line is down 1, right 1, down 1, right 1. So this line is y is equal to negative x and then plus 1, because that's my y-intercept. And then this is a parabola, and it looks like a pretty basic parabola. It's just shifted 1 unit to the right. So this would be y is equal to, so off the parent function, x squared, you're shifting it 1 to the right, so it'd be x plus 1 all squared. And it looks like that shift happens at 1 this time, not at 0. So let's see how this is going to look. This is going to be negative x plus 1 when x is less than 1. And then I'll just include it on the bottom one here. It's going to be x minus 1 all squared when x is greater than or equal to 1. All right. You don't have to be proficient at like doing exactly this, but you will see piecewise functions, and just understand that they are components of other functions, just combined. Okay, that's it for functions. On to exponentials and logs. It turns out that 2 plus 4 is not 7. It's 6. It happens to all of us. I'm telling you, 6 times 7 is 43 some days. I get it. What we've done so far is a lot of polynomials, rational exponents, radicals, and rational functions in general, like divisions or ratios of polynomials. AKA, we've done x stuff to numeric power stuff. We've done a lot of that. X to a number, x to a number, x to a number. We're doing the reverse now. We're going to do a number to the power of x now instead. Basic exponential functions are covered in Algebra 1, but you can do a little bit more with it. You'll see in 32. And then logarithms are the inverse of that, and you can do even more with it going backwards. So that's what we're going to do. Let's keep the party going. Identify the following functions as either exponential growth or exponential decay. Just a little warm-up. All these numbers that are raised to the power of x determine if it's growth or decay. If your value is greater than 1, it's growth. If it's less than 1, or in magnitude, or positive value, I guess, so between 0 and 1, non-inclusive, then it's decay. So here would be growth. Here would be decay, right? 2 is greater than 1. 1/2 is less than 1. Here I try to be slightly extra. This is growth because pi minus 2 is 1.14-ish, which is greater than 1. And then here, oh, I forgot the y is equal to. Anyway, it's going to be 5 times 1/2 to the power of x. Actually, that's the same exact function as a. So this is also except it had a negative exponent. So there's the difference. It's decay because if you take that negative exponent, that's just the reciprocal, you bring it down to the denominator, make it positive. It turns to a 1/2. So I guess it was a little misleading for me to have highlighted that 2 there. It's really this 1/2 after we kind of factor in that negative exponent. That's decay, and 1/2 is less than 1. Okay, a little confusing on that last one there. Yeah. So the big thing is just kind of knowing what the shape of the graph looks like. If it's growth, it looks like that. If it's decay, it looks like that. Okay, so consider the compound interest formula. You don't have to memorize this formula, but what this is it's a doorway, a gateway to a very important number that is a transcendental constant that is useful. You actually need to know it. So I introduced phi earlier, which is that 1.618 number. That's not useful. That was a for fun thing. Here, you need to know this number. So if you were to have n run to infinity, and okay, and then plug in 1 for p. So this is compound interest. The amount of money you make is your principal times just kind of how your money compounds in a bank. So what we're doing is we're just putting $1 in, and we're making our rate also just a fixed 1 as well. And we're amping up n to infinity, and we're just saying over 1 time interval. So we're just keeping everything pretty simple. And what we're going to do is we're going to make this n really large. And actually I can do this pretty easily here. I can prove the number. That's dead center, isn't it? I guess I don't really need to show that expression, but okay, so on Desmos, what I can do is this. Well, it does help. So I'm going to take this expression, I'm going to plug it into Desmos, and I'm going to actually naturally derive the number that we'll start with n is equal to 1, and we'll just go up to like 1,000,000. I want to show here. Okay, so I'm cranking this up to infinity. Unfortunately, I can't plug in infinity. So I'm just going to get really, really close. And as I crank this knob up, there it is, sort of. Not really. This number right here is the number e. That thing. Which is another transcendental constant. We use this. This is just a really important number in calculus and differential equations, which is a chapter of calculus in its own class even. You'll have to wait to calculus to really see it shine. I really don't think. What we technically did was we just took a limit, which is a calculus idea. We just ran this limit to infinity, and hey, we got e. This is a number. It's 2.718. You don't need to know what it is, but that's the derivation. It comes from a formula you did in pre-calc. It just really shines in calculus. Okay. So that's it for that. Now we're just going to solve some exponential equations. So for exponential equations, you can utilize the logarithm, which is yet to come. So right now I'm just going to pretend we don't know it, and I'm just going to solve these problems by using the same bases. Here, this is 2 times x, or to the power of 2x plus 1, and this is equal to, well, I know that 32 is 2 to the 5th power. So what I can do is I can just set the exponents equal to one another and then solve from there. So 2x plus 1 is equal to 5, so then x must be equal to 2. Feel free to plug it in to test if you'd like. All right, over here, this is 3 to the 1st power, and this is 3 to the x plus 1 power. So this would be, well, you're just adding the exponents. This would be 3 to the x plus 2 power, and 27 is just 3 to the 3rd. So again, you're just setting those exponents equal to each other. And you get x plus 2 is equal to 3, so hey, x is equal to 1. Not too bad. Okay, next up, you'll notice that this base 3 and base 4, they've got a lot in common. So I'm going to divide out that 3. And as I divide that 3 out, I'm going to notice this is going to turn into an 8. I can turn this 4 not into an 8, but I can turn this 8 into a 2 to the 3rd. I'll show you what I mean. So this x and this 3, they're going to multiply by one another to get 3x. And we kind of run into this issue because 4 you can't raise to at least a natural numbered power to get 8. So you got to get a little crafty here. We can change these both to base 2. So this 4 is the same thing as 2 squared all to the 3x. And this 8 is the same thing as 2 to the 3rd. Now I can set these equal to each other. I can set the, well, it's going to be 6x equal to 3. And I get x is equal to 1/2. Okay, last one, e to the x is equal to 0. Yeah, so this is actually another exponent property that we didn't really talk about earlier. Any number other than 0 raised to the 0th power is equal to 1. So here, x is equal to 0. E to the 0 is equal to 1. You could take the natural log of both sides, which is the inverse of e to the x. So we're going to be writing log expressions very soon. May as well apply it now. So natural log, it cancels on the left side because those are inverses. So x would be equal to the natural log of 1, and the natural log of 1 is none, is 0. We're gonna write down these properties. Natural log of 1 is 0, and then there's one more natural log that you need to know. So that's the inverse of e. Anyway, okay, so logarithms, the way that logs work is, this is our base. So this will be log base 5 of 125 is equal to the exponent, 3. So here it'd be log base 16 of 64 is equal to the exponent, 3/2. See if you can beat me on the next one. Should have got log base 3 of 1/9 is equal to -2. Cool. Eventually we're going to be doing some log properties down below, and I'm jumping around a little bit, but it'll be worth it. We're going to do this fancy little trick eventually to bring this 2 up front. I just want to prove it real fast. So this would be the same thing as log base 3 of 3 to the -2nd, if you think about it, right? Because 1/9 can be rewritten as 3 to the -2nd. So this -2 can be brought up front. So you have -2. Log base 3 of 3 is equal to -2. I'm just having fun with logs. Log base 3 of 3, this would be like asking 3 raised to what power is 3? Well, that's just 1. So -2 is equal to -2, and it kind of works out. Log properties are weird when you first play with them. Like if that was weird for you, you're not alone. But I would say fall back to just like the definition and then apply the properties as you see fit. And you start to see how they do really behave in an inverse way that they do for exponents. So for like example, for the narrative here, I'm just going to do b next, 35b. We know that with exponent powers, when you have the same bases, you would add the exponents, right? And if you're multiplying the bases. So here, we're adding the expressions, so we're going to multiply what's on the inside of the logs. It behaves in the exact opposite fashion. So here it'd be log base 2 of 3x. If you're adding logs, you're multiplying what's inside of them, which is the opposite of if you're multiplying exponents, you're adding the powers. Same thing here. So, if you're dividing exponents, you're subtracting the powers. So for C, if you're subtracting the logs, you're dividing what's inside of them. So this would be log base 3 of 4x over 2, which is log base 3 of 2x. Okay, jumping back to 34D, this one's really silly. It's just saying E is equal to E, which is like, yeah. But if we write this as a log, it'd be log base E of E is equal to 1, which we kind of just saw that over here. Log base E is the same thing as the natural log, so that's kind of the point of this problem, is to introduce this ln notation. So that's maybe, I sometimes say I'm calling my friend Alan for help, maybe when we're doing partial fraction integrals, which is in Calc 2. Anyway, so this would be the natural log of E is 1. So you don't need to know much about E. Like, you don't need to know what E squared is equal to, or the natural log of 2. You don't need to know what any of those things are. But you do need to know the natural log of 1 is none, and the natural log of E is 1. The natural log of E is 1, the natural log of 1 is none. It's the same thing with normal log. So if I had the log base 2 of 1, that's just 0. And if I had the log base 2 of 2, that's just 1. Those are log expressions I expect you to kind of know. Okay, where am I at? Where's my cursor? Hello? There we are. For 35. Okay, natural log of E. Actually, I scroll down beyond kind of where I had my cheat sheet here. The natural log of E is 1, and the natural log of 1 is none. This goes to 0. You can technically... So you can identify natural log of 1 as none and it just goes away. Or you can just kind of have fun with it. Like here, the natural log of E minus the natural log of 1. This would be the natural log of E over 1, which is just the natural log of E. And that's just 1. So you could use the property first if you want to, but it's kind of a waste of time. You could have just canceled it. And then over here, this pi just kind of gets slapped up front. So this will be natural log of x to the pi and then plus 1. I was just having fun with the pi. It's a number. So yeah, you can do number stuff with it. So pi is different than E, but they're both considered transcendental constants, which is just fancy irrational numbers that our universe is speaking to us with. And we discovered. We did not create the numbers. We discovered them. Okay, that's my opinion, man. All right, looking at 36. Solve the following logarithmic equations. So we're just working backwards. So like here, we're just saying, okay, well, first off, I can use a log property to get log base 4 of x squared is equal to 1. And then I can just use the definition of a log to rewrite this. So this would be base 4 to the first power is equal to x squared. And now I'm just taking the square root of both sides. I got to be careful here, though, because I'm getting a plus or minus 2. And this negative 2 is known to be extraneous. You cannot put a negative number into a log. Actually, take a look at this graph right here. This is the graph of log base 2. It's a different base, but it has the same shape. You'll notice that there is an empty void here. Just like how the exponential, if it's like, say, 2 to the x, never gets negative, right? Think about 2 to the x. I can raise 2 to the first, second, third, fourth, fifth, negative numbers even, but I just get fractions from that. We actually saw that in part D above, if you remember this one, if you had a negative, well, I don't really want to compare it to that. Never mind. Point is, we don't hit any negative x values, any negative y values for the exponential. Likewise, we don't hit any negative x values for the logarithm because they're inverses one another. So x's are switched with the y's. So if you consider 2 raised to any number you want, you cannot make that a negative number. Try, right? It's not possible. All right, you go super negative, that's just going to be a fraction. We can't get negative numbers. Likewise, same exact thing, but for logs as inverses, we cannot get negative numbers. So what am I yapping about? What is this guy yapping about at this point? The negative is considered to be extraneous and not, it's like extra, that's what extraneous means, and not a part of our solution set, which is just x is equal to 2. You cannot feed in a negative number into this log. Anytime you are asked to do that, it's undefined. It's defined on the imaginary in the complex plane, but not. We're in real life here, and just real numbers. Remember, that's calc, all real numbers. If you want to do imaginary stuff, go to complex analysis. Okay, looking at B, this is going to be log base 2. Let's use a log property here. If you're adding the logs, you're multiplying what's on the inside. Log base 2 of 4x equal to 5. Now we're just going to use the reverse definition of a log. So this will be just 2 to the 5th is equal to 4x, or just definition of a log. So this is just switching. To be clear on what we were doing here, we switched from exponential form to logarithmic form over here. Now we're switching from a logarithmic form to exponential form. So notice kind of how this was a base 5, this was a base 5, this was the exponent 3, this was the exponent 3, this was what we were taking the log of, and it just follows that same exact thing. Base 2, exponent 5, what we were taking the log of, same pattern. So fall back. If logs are like, what is going on? If that's what you're thinking with logs, you're not alone. Fall back to just the big definitions. The definition of a log, understanding how this exponent behaves, add, subtract, that's it. Just those 4, and you'll be fine. Okay, and then this one, you're dividing on the inside, so this will be log. We don't know the base. So when you don't know the base, it's assumed to be 10. Depends on where you are, though. I've been in spaces where it is assumed to be 2. I've been in spaces where it's assumed to be E. So it depends on where you are. If you're in high school or it's like your first run through of calculus, it's probably assumed to be 10. But if you're in grad school, it's probably assumed to be E. And if you're in grad school, why are you watching this video for math? And if you're in, I think some people in some CS courses assume base 2 here. Okay, for binary. All right, let's see. So technically this is like 10 to the 0th is equal to x, but it doesn't matter what the base is, right? Because we know that the log, whenever the log is equal to 0, then it must be 1 on the inside. It doesn't matter if it's a natural log of 1 is equal to 0, if it's log base 2 of 1 is equal to 0, or log base 10 of 1 is equal to 0. The point is you're raising a number to the 0th power, so that will always be, except for when it's 0, but it'll always be 1. Yeah, so like we're kind of running into these little moments where we have like a 0 to a 0. We talked about 0 over 0, like very briefly in the rational expressions. Calculus answers these problems. We start to do, like they're called indeterminates, and we eventually we face them, and we say you've got to figure your stuff out, man. Determine who you are. We don't say that. Okay, touch withdraw. Did I turn that off? All right, looking at D, we can bring this 1/2 up as the exponent. So this is the natural log of x to the 1/2 is equal to 1. We can rewrite this using the definition of a log, right? This is a log base e of square root of x is equal to 1. Now we're cooking, right? Now we're talking precalculus. So this will be e to the first power is equal to the square root of x. We can square both sides to get a final answer of x is equal to e squared. As always, you can plug it back in to like check to see if it's right. I don't know. I just feel compelled to for some reason. Natural log of e squared is equal to 1. Is this true? It sure is. Bring that 1/2 up front. This is the natural log of e is equal to 1. And hey, we showed that before. We showed that. Yeah, and something, it may not be a bad idea to replay or rethink and pause. I'm saying that very late in the video, but I think this is kind of some of the trickier stuff. Okay, identify the asymptotes for each of the given functions. Okay, yeah, all this is really drawing attention to is that we have an asymptote here and we have an asymptote here, right? You can never get 0 from 2 to any power, right? 2 to the negative millionth power is like 0.0000000, and eventually you're going to see a number there. You can never get 0 out of this. So that's an asymptote. Here we have a horizontal asymptote at y is equal to 0. And then here we have a vertical asymptote at x is equal to 0. These are inverse functions of one another, right? You get that really kind of cool, yeah, inverse. You like my drawing? Woo! We're doing great. effect here with this, and I'll just graph it this way because it's a lot more satisfying to see. Not my scribbles. Oh yeah, they don't even intersect. Ignore that. But here you get that symmetry over y is equal to x. Here I'll make this dash to make it look fancy. Okay, chapter 7 down. Let's move on to chapter 8. I didn't finish 2 problems. I'm going to do that real fast. This one ended up coming out to be just the log of x squared. And this one, okay, this is just 32 is equal to 4x. Was that bad? Divide both sides by 4? Is that really what you're complaining about? Me, who's proof checking right now? Anyway, okay, now moving on to trigonometry. Chapter 8, trig, everyone's favorite, right? Waves are everywhere. You are seeing and hearing me through the wave, right? Sound waves and how photons refract off light or something like that, light waves, right? So waves are important. Trigonometry gets a bad rap. It's like with verifications and proofs and identities, and man, that's a shame because they're very useful in our life, and we experience them all the time. So we have a negative relationship with it. Hopefully I can change that a little bit. All right, so the unit circle. The unit circle is an essential component. It's just a circle, man, of radius 1. We actually already saw this equation. It's x squared plus y squared is equal to 1. If you were to graph this on the Cartesian plane, x squared plus y squared, 1. You just get a circle. Okay. This is the unit circle. It's not, the unit circle is not this like magical thing that exists somewhere else. And what we're doing with it is we're just drawing some triangles inside of it. You know, geometry's got a thing for triangles and circles. So, and really these are triangles that you know and love. So for example, in orange here, I'll do this triangle right here. So this is actually a 30, 60, 90 triangle. This is 30 degrees. This is 60 degrees. This other one right here is also a 30, 60, 90. It's just that the 60-degree angle is created, you know, on the other side. So those should sound familiar. If you remember the ratios for that, x root 3, and then 2x, that's a good sign. Likewise over here, I don't want to do, maybe I want to do like pink or something. No, purple. Over here, we actually have a 45, 45, 90 triangle. So why am I bringing these up? This is 45 degrees and this is 45. What we're doing is what we did in high school is in geometry, we introduced 30, 60, 90s and 45, 45, 90s. And really what that really served the purpose of is, one, we see 45, 45, 90s like kind of often in real life. Like anytime there's a diagonal on a square, that's a 45, 45, 90 triangle. And 30, 60, 90s are relatively common too. And these are just like major important values that are angle values that can help us convert to like a trig expression. So I'm going to keep going here in my explanation. All right, so degrees are great, but radians are better. So if you consider the circumference of this circle of radians 1, the circumference formula is 2 pi r. If your radius is equal to 1, then your circumference is just 2 pi. So what we do is we consider a full rotation to be 2 pi instead of a 360. Whoa. So I just did a 2 pi rotation, not a 360. And now I'm slightly dizzy, but only one. It's not gonna. I can handle one spin. Okay. So yeah. Just keep that in mind. So if I want to do half that, that's pi. If I want to do a quarter of that, that's pi over 2, which is slightly confusing, but it's what it is. What else is there to take away? So from, say, like the 30, 60, 90, we know that this radius is, or this, and actually, yeah, I'm gonna do one of these, okay? I'm not gonna derive the whole unit circle. I'll be done with this in hopefully just a couple minutes. 30, 60, 90, hopefully you remember within a 30, 60, 90, that if your side opposite to the 30 is x, and your side opposite to the 60 is x root 3, this would be a 2x. So if you know your radius is 1, okay, well, you would divide by 2 to get this length of half, and then you would take this 1/2 and multiply it by a root 3 to get this length right here. And what you're actually getting is you're getting, so let's see, the root 3 over 2 would be the x value because it's x is left, right. And then the up down is 1/2, right? You're getting the x and y components of, that little location on the unit circle. Over here, this is just 1, 0, right? It's just the x-intercept. Nothing too crazy. And this pattern continues. You can do the same thing. I'll just do it with this 45, 45, 90 as well. So I'm going to take this 45, 40, and this will be all the derivation I'll really do. I just want to show that this isn't just some made-up thing. That's all. So for a 45, 45, 90, we have an isosceles triangle. These are actually the same. So this would be x, this would be x, and this would be x root 2. So if you know that the hypotenuse is 1, then you would divide both by root 2. So this would be 1 over root 2. This would be 1 over root 2. You can rationalize these to get root 2 over 2. We saw that a little earlier. And then root 2 over 2. So this ordered pair would be root 2 over 2, comma, root 2 over 2. Same pattern exists for this one, just they're flip-flops. This is 1/2, comma, root 3 over 2. And by the way, remember these are, we're in radians, right? That was the whole point of this little 2 pi talk. So instead of it being 30 and then 45 degrees and then 60 degrees, we tend to view this as pi over 6, pi over 4, and then pi over 3, respectively, to the other values I said. And then lastly over here, this is just 0, 1. I just suggest knowing the first quadrant. And then just using patterns for the rest. I don't have the sine of 5 pi over 3 memorized. Bottom line. I honestly don't have a lot of trig functions memorized. I think I have like a sine of 0 memorized. Sine of 0 is 0. Everything else I just like naturally derive on the spot, because that's where memory isn't as useful as just understanding the concept as a whole. Anyway, I'll get off my pedestal here. All right, what else can I show you? So yeah, this would be, so let's just keep looking at this 30, 60, 90. Where do sine and cosine come into play? SOHCAHTOA? Yeah, SOHCAHTOA, anyone? So we have this, I'm going to just redraw this triangle here. Going to redraw it. And, instead of writing 30, I might just write pi over 6 instead. Anyway, we know that this radius is 1. We know that this distance is that root 3 over 2. And we know that this is 1/2. So, SOHCAHTOA. SOHCAHTOA. This is a little acronym, kind of how we defined sine, cosine, and tangent back with right triangle trig. So everything's kind of coming together. If I have the sine of an angle, in goes an angle, out shoots a ratio of sides. It would be opposite over hypotenuse. So it would be 1/2 over root 3 over 2. And what is my angle here? Well, my angle is the pi over 6. So the sine really just, pi over 6, here we go. Oh, no, so opposite over hypotenuse, sorry. Hypotenuse is 1. I don't know why I put it over the other value. So it'd be 1/2 over 1, there we go. So the sine of pi over 6 is equal to 1/2. And then for the cosine of pi over 6, remember this is adjacent over hypotenuse. So it would be root 3 over 2 over 1. That would mean that the cosine of pi over 6 is root 3 over 2. So from our right triangle trig days back in geometry, and using 45, 45, 90s and 30, 60, 90s, we can build the unit circle, which is just a circle of radius 1. That's all that little, I don't know, what was that, 7-minute blah was about, is that what you should do for calculus is not burn this into your memory, but instead understand the concept. I have a better video of this. It's like a 30-minute video. It's called Unit Circle for Dummies. I recommend watching that. This was a really quick version of that. The last little fun pattern I want to draw attention to is, check this out. This is a 0, right? This is 1 over 2, right? This is a root 2 over 2, right? This is a root 3 over 2, right? And this is a 1, okay? All right. So have you ever thought about these the following way? Because I love this. The moment I saw it, I'm like, whoa. This is 0 over 4. This is, oh, not 4. Yeah, this is 0 over. This is root 0 over 2. This is root 1 over 2. This is root 2 over 2. This is root 3 over 2. And this is root 4 over 2. Because that's root 4 is, 2. And 2 over 2 is 1. So kind of a cool pattern. These are just, it's just churning through the square root of 0, 1, 2, 3, and 4. And you can actually see that in reverse for the x value. 0, so root 0 over 2, root 1 over 2, root 2 over 2, root 3 over 2, and then root 4 over 2. Look for patterns, people. That's what is going to help that I guess pseudo-memory piece, but really it's an extension of understanding the concept as a whole. So I'm going to say know the unit circle pretty well, and then just use like symmetry and intuition to figure out the other values. So stick to the first quadrant for sure. Okay, yeah, that's good. 10 minutes on that sounds fair to me. All right, so I'm going to be evaluating some trig expressions now. So yeah, I mean, I liked every time I encounter a moment where I have to evaluate a trig expression, you might, I don't know if you're a student of mine, you might see me like drawing like a little unit circle kind of off to the side because I just build it kind of in my head. Like I don't have them memorized. So like the sine of pi over 3, I still don't have this memorized. Maybe I should probably as a teacher, but memorize these. So pi over 3 is right here. So maybe the last little hint I'll give you on the patterns. I would clump all of your over 6s together. So this is over 6, this is over 6, this is over 6. So all these blue lines that I'm drawing are over 6. So I'll kind of walk you through that a little bit more clearly, I guess. This first line here is 0 over 6, then it's, 0 pi over 6, 1 pi over 6, 2 pi over 6, which is pi over 3, 3 pi over 6, which is pi over 2, these are for the angles, 4 pi over 6, 5 pi over 6, and then this is 6 pi over 6, which is pi, right, 1 over 1, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, and then 12 pi over 6, full circle. 12 over 6 is 2, right? And then also to split this up with the quarters. So this is 0 pi over 4. This is 1 pi over 4. This is 2 pi over 4. This is 3 pi over 4. This is 4 pi over 4. 5 pi over... No, not that one. 5 pi over 4, 6 pi over 4, 7 pi over 4, and then back to 8 pi over 4. So... yeah, I don't know. That could help too. All right. So for 39a, we have the sine of pi over 3. So that would be, this ordered pair right here. And sine, so it cosines the first value, and then sine is the second, kind of just how we saw it with the triangle I drew over here. So cosine, this would be root 3 over 2. Cosine of pi over 6, we actually just evaluated that. That was also root 3 over 2. It's, remember, this triangle, these are both just 30, 60, 90s. One is just a 60, 30, 90, if you want to think about it that way, just oriented in a different way. So 3 pi over 4, that would be this one right over here. So we're leaving the first quadrant. I know that this is going to be root 2 over 2, comma, root 2 over 2. But one of them's negative, right? And it doesn't matter which one, because tangent is just ratio of sine over cosine. You could have saw that definitely over here, right, with the tangent of, say, pi over 6. Here from this angle, you would have done opposite over adjacent, which is 1/2 over root 3 over 2, which is the sine value of 1/2 over the cosine value of root 3 over 2. So here we know they're the same things, right? So it's root 2 over 2, comma, root 2 over 2. And, well, the x value is negative because we're on the left side of the y-axis. So anything over itself is just 1. This is just negative 1. So that would mean that the tangent of pi over 4 is just 1. Okay, sine of 5 pi over 3. I do have to kind of think about this one a little bit. So let's see, 5 pi over 3, that is, it's in the 4th quadrant. So this one is 6 pi. So let's see, I would do this. I would do 5 over 3 is 10 over 6. So this is 11 over 6. This one's 10 over 6. So I'm right here on the unit circle. And I know that this is the same as this ordered pair, just the y value is negative. So it's 1/2 comma negative root 3 over 2. So sine, cosine, sine is the second one, negative root 3 over 2. I mean, I'm solving these, not for the first time, I'll be honest. I've solved them before, but so I'll even like kind of just check. But yeah, negative root 3 over 2. But the idea is that this is like my authentic problem solving. This is how I'm doing it if I'm in the moment, you know, drawing a circle and then I'm just problem solving. Okay, so for E, you'll notice that this is a negative angle. So negative angles just go clockwise instead of going counterclockwise. So it would actually be right here. It's this little point right here. You can think about this also as just adding a full rotation. So this would be the same thing as cosine. So if you did negative pi over 6, a full rotation is 2 pi. So that would be negative pi over 6 plus 12 pi over 6 to get 11 pi over 6, which is, again, this location right here. This is the same thing as a cosine of 11 pi over 6. I don't know if that helps. You could think about it as just going pi over 6 radians clockwise, or you can do add a full rotation and you're just back to where you started. That's why you get that wave effect, that up and down kind of over and over and over again, because after a full wave, you're just redoing the same thing. You're just going round and round. Anyway, the cosine value is going to be the x value. So that would be root 3 over 2 again. Lots of root 3 over 2s for this little half. Okay, and then the next one, what is this? So this is over a full rotation. I can subtract a rotation if I want to. So if I did 13 pi over 6 and then I minus a 2 pi, which is a 13 pi over 6 minus a 12 pi over 6 to get pi over 6. So this would be the same thing as the tangent of pi over 6. Yeah. Yeah. So a tangent of pi over 6 would just be the y over x of those values. So that would be 1 over root 3 or root 3 over 3. Right? So I'll simplify that for you. It'd be 1/2 over root 3 over 2. The 2's cancel. So that's 1 over root 3. This is fine to leave it as this, but if you rationalize it, it'd be root 3 over 3. I'm a teacher that's okay with 1 over root 3, but you know, some teachers need you to rationalize, I guess. Okay, so you have reciprocal functions. So we looked at, consider how a triangle has 3 sides. And we looked at opposite over hypotenuse, we looked at adjacent over hypotenuse, we looked at opposite over adjacent. But what about the reciprocals? Technically, there are 6 ways that you can match up 2 out of 3. It's a combinatorics problems. 2 out of 3 of the objects. You could do hypotenuse over opposite. You can do hypotenuse over adjacent. You can also do adjacent over opposite. So there's 3 more combinations or setups that you can do. So that spawns cosecant, secant, and cotangent, the co-functions. That's not true. Secant's not a co-function. 2 of them are co-functions. Cosine's the co. Anyway, it spawns the reciprocal functions. That we can call them. So cosecant is the reciprocal of sine. So we're actually just taking the reciprocal of this. So this would be 2 over root 3, which is, in my opinion, fine to leave this way. But some people say, hey, you have to rationalize that. Where are you going, kid? You're going to end up at McDonald's if you don't rationalize denominators. Okay, so you get 2 root 3 and then over 3. Okay, this one is just the reciprocal. Yeah, what do we got? We just did g, right? Yeah. So this would just be the reciprocal of what happens at the cosine of 0. So the cosine of 0 is, yeah, so I can even do this. 1 over cosine of 0. The cosine of 0, cosine's the first value is just 1. So 1 over 1 is just 1. Looks good to me, right? I could have done the same thing over here. I could have just said that this is 1 over sine of pi over 3, which is that expression. I could have done that. Okay, so this is just the 1 over tangent of pi over 4. So the reciprocal functions, reciprocals, right? So that would be right here, this root 2 over 2 over root 2 over 2, which is just 1. Yeah, another 1, 2 ones in a row, right? Okay. This one right here is 1 over, so the reciprocal cosecant is again sine. So 1 over the sine of 7 pi over 6. 7 pi over 6 is right here. So this would be, another way I think about it is like this is longer than this is taller. So the x value would be the root 3 over 2 one. And then since it's also negative, this is also negative here. Anyway, like this is longer. This horizontal length is longer than this vertical length. So I know that the x value is bigger than the y value. That's how I remember them. You can also just do, it's the exact opposite of this one. You got so many different ways. That's the beauty, is that I didn't learn about the little trick I showed you in gold here. I didn't learn about that till like 2 years ago. And I'm like, whoa, that's cool. Patterns are awesome. So look for them. All right, so sine of pi over 7 pi over 6, it would be the negative half. So it'd be 1 over negative half, which is just a negative 2. All right, the next one is 1 over cosine of 7 pi over 6. Lucky for us, we already have that 7 pi over 6. So it would just be 1 over the negative root 3 over 2, which is... I do have a problem with complex fractions. If you do a fraction and a fraction, I'd prefer you not do it that way. But I'd be cool with you doing 2 over root 3, like negative 2 over root 3. I think that's fine. But if you rationalize that, it'd be negative 2 root 3 over 3. If you chose to rationalize, which I wouldn't need that. I would be fine with negative 2 over root 3. So you're just doing the reciprocal of that expression right there, because it's a reciprocal of cosine. All right, the last one, cotangent of pi over 2. So this one's a little weird. I'm actually not going to put this equal sign here. I'm going to say it's, because there's a bit of a nuance, this is like 1 over the tangent of pi over 2. But we have a problem with the tangent of pi over 2, because pi over 2 occurs right here. Tangent is sine over cosine, y over x, which is 1 over 0. And that's a problem, right? That's undefined. That is not an indeterminate. That's just an undefined value. So we have 1 over undefined, which is kind of like infinity. So this is like 1 over 0. This is bad math, but it's good to demonstrate the concept. The tangent of pi over 2 has an asymptote there. It doesn't exist. You cannot do 1 over 0, but you can do 0 over 1, which is just 0. So actually, this is just straight up 0. Cotangent is x over y, not y over x. So you could have just, you didn't have to do this fancy 1 over 0. You could have just done 0 over 1. It's the same thing. Yeah. Yeah, this is one of those things too where I would, you know, it's a lot to unpack all at once. Like, how much trig did I just teach in 22 minutes there? I mean, like a whole lot, like weeks. So, you know, give it some time. But I would say bottom line is you got to know the first quadrant. You can't, and you got to know the reciprocal functions. I'll give you a whole list of all the identities you need to know in this little section right here. So real fast, before we dig into solving trig equations, just want to show you the graphs. You should also kind of know the graphs a little bit as well. So the sine of x, just taking a look at that. We know that sine of x is your y values as you kind of go around the unit circle. So you'll notice the y values go from, let's just look at the major 4 moments, 0 to 1. So this y value is back to 0, and then to 1, and then back down to 0. So for example, at a theta or angle value of 0, 0 is our output. So that's why we start at 0, 0. For a theta value or an angle of pi over 2, our y value is 1, pi over 2 comma 1. For our angle value of pi, that's halfway around the unit circle, our output is 0. Our y value is 0, so that's why you see pi comma 0. And then lastly, for the little first rotation, I guess, we can see here that at 3 pi over 2, the y value is -1. It's the lowest part of the circle, so that's why you see 3 pi over 2, -1. And when you finish the cycle and you go back to where we started, after a full rotation, 2 pi, you're going to see 2 pi comma 0. And it just does that forever, because round and round we go. So you can do this with cosine as well, what cosine looks like. And then tangent, I just want to show the asymptotes for tangent. So we saw x is equal to pi over 2 as an asymptote, right? And that's because we don't like dividing 1 by 0. We don't like divided by 0. So when your x value is 0, that's bad. Same thing with 3 pi over 2. So you'll see x is equal to 3 pi over 2, not w. There it is. It's also an asymptote there. Okay, we're going to solve some trig equations now. Let's do it. Let's do it. Let's do it. Let's do it. So if we're solving these trig expressions, we're just trying to figure out, so we're just doing it in reverse. If we're given the ratio of sides, what would be the angle at which that is achieved? So where on the unit circle is our y value equal to pi over 2? Well, that, not pi over 2, root 2 over 2. That happens right here at our pi over 4 value. So since we know the sign of pi over 4 is root 2 over 2, we just say x is equal to pi over 4. Now, here's the thing. That's just the first solution. There are more solutions where our y value is equal to pi over 2. You also have a solution right here because our y value is still positive. So that would be at 3 pi over 4. So technically you have an infinite number of solutions, right? Because you can just keep going round and round and round. That's why generally you'll see like a domain restriction for this. So for this one, you just have those two solutions, pi over 4 and 3 pi over 4. Over here, you have to solve for cosine first. So I'm going to add the 1, divide the 2. So cosine of x is equal to 1/2. And then x is going to be then equal to, well, let's see. Where on the unit circle do we have an x value of 1/2? That would be right here and right here. So that would be at pi over 3, and this one's a little hard. I don't really like thinking about this one. Is that 5 pi over 3? So this would be pi. This would be 7 pi over 6. This would be 8 pi over 6, 9 pi over 6, 10 pi, yeah, 5 pi over 3. So you would get pi over 3 and 5 pi over 3. Cool. All right, so this one's a little different because now I've changed the frequency up a bit. So when you are taking the tangent, cosine, sine, whatever of not just x but now 2x, you've changed the frequency. So since the frequency has changed, it's either gotten faster or slower. If you multiply by a bigger number, it gets faster. If you divide it out by a number, it gets slower. So this is going to happen more frequent, twice as frequent actually. And you'll see how that's going to impact our solutions. So when is tangent equal to 1? Well, in general, it's here and here, because that's where you get the root 2 over 2 comma root 2 over 2 business. And you get that negative on the left side, so negative over negative is a positive. So you're going to be getting, now here's the thing though, 2x. So we're taking the inverse tangent right now, and we're undoing this tangent. We're taking the inverse tangent of both sides, and it canceled on the left side, and we're getting the solutions from 0 to, just in general, I'm going to go a little past 2 pi because you're going to see in a moment this divide by 2, is we're going to get pi over 4, and we're going to get 5 pi over 4. But I have to keep going because I'm going to divide by 2 here, all my solutions. So I have to go another rotation to see the fact that since I have an increased frequency, it's moving quicker, I'm going to be hitting these values more frequently. And we're going to see a similar story, but in reverse for a later problem. So you have to add a full rotation to this pi over 4. That would be 9 pi over 4. And then add a full rotation to the 5 pi over 4, which is 13 pi over 4. And then now I divide everything by 2. Divide by 2, divide by 2, divide by 2, divide by 2. So my solutions are pi over 8, 5 pi over 8, 9 pi over 8, 13 pi over 8. And if I did keep going, it would be outside the bounds from 0 to 2 pi. The next one would have been 17 pi over 8, which is larger than 2 pi. So it would be outside of the solution. So no need for this comma here. Those are all my answers. I have 4 answers for that one. Okay, so for cosecant, I'm going to divide here by 4. Just that's a coefficient just sitting in front. So when is the cosecant of x equal to 2? This is similar to when is the sine of x equal to 1/2. And where does that happen on the unit circle? That happens, so y value of 1/2. Y value of 1/2, that happens here and here. Yeah, so it's going to be at pi over 6 and then 5 pi over 6. Right, for 40D. Fun. Okay, this one over here, secant, so it's reciprocal. This is similar to when is cosine of x over 2 equal to the reciprocal. So it would be 1 over root 2, which is root 2 over 2. It's a more familiar unit circle expression. So that was the reciprocal I just did. I just rationalized it. And now we see this x over 2. So we got to be a little bit more careful here. Similar to C, where we have a frequency change. So this is slower. We're going to be seeing less values when this happens. So when is cosine equal to pi, root 2 over 2? Well, that would be at like here and here. So it'd be at like pi over 4 and like 7 pi over 4. But here's the thing. We're multiplying everything by 2 now. Multiply by 2, multiply by 2, multiply by 2. So this value, this second one, is just going to be too large now, because we're going to get 14 over 4. That's greater than 2. So we're actually removing this solution because it's not quick enough. So we actually have half the number of solutions we normally do for a halved frequency. And we had twice the number of solutions that we normally do for a twice as fast frequency. Hopefully that makes a little bit of sense. So I'm just getting x is equal to 2 pi over 4, which is pi over 2. And for the last one here, when do we get a ratio of x? Remember, cotangent is x over y, right? When do we get 0 over 1 on the unit circle? When do we get a 0, 1 or 0, -1, right? That would work just the same as well. That would be at pi over 2 and at 3 pi over 2. So final 2 answers here. And these are also the asymptote. You could have thought about it the other way. When you have tangent of x equal to like the reciprocal of 0 over 1, which is like 1 over 0, aka where are the asymptotes for tangent? Pi over 2 and 3 pi over 2. We just saw that. We just saw it. Here we are. Pi over 2, 3 pi over 2. And you know, you can also, whatever, while we're graphing, I guess, cotangent of x. Okay. Pi over 2, 3 pi over 2. We were seeing when it was equal to 0, right? There it is. All right, lastly, the trig identities that you need to know are, for calc, you need to know, so the reciprocal identities, the quotient identities, so we just did a quotient identity. Tangent is sine over cosine. Cotangent is cosine over sine. So you need to know there's 2 quotient identities, tangent and cotangent. There are 6 quotient identities. Right? Not quotient, reciprocal. That's just the reciprocal. So cosecant's the reciprocal of sine, secant's the reciprocal of cosine, and cotangent's the reciprocal of tangent. And then you need to know the Pythagorean ones. There's 3 Pythagorean identities, which I'll throw somewhere here. So the Pythagorean identities are, so it's like the Pythagorean theorem. Sine squared x plus cosine squared x is equal to 1. Think about how this makes sense. It's just Pythagorean theorem, which you can apply over here. So like, for example, root 3 over 2 squared plus 1/2 squared is equal to 1 squared, right? I just used these values. And sure enough, that is going to be true. That's going to be 3 over 4 plus 1 over 4 is 1. So that's all that's really saying, is that that's always true no matter where you are on the unit circle. And then you can also divide. If you divide everything here by, say, cosine, you would get tangent. Sine over cosine is cotangent. How about we divide everything by sine? If you divide everything here by... No, I want to do cosine. I like that. If I divide everything by cosine, sine over cosine's tangent. So there's tangent x plus cosine squared over cosine squared would just be 1. and then 1 over cosine would be secant. So I recommend knowing these as well. And if you take the original and you divide everything by sine, you would get 1 plus cotangent squared x is equal to cosecant squared x. Lastly, if you take Calc 2, like later half of Calc 2 and then definitely Calc 3, you should know power reducing, but you will not need to know these two that I'm about to write down for Calc 1. At least you shouldn't. Power reducing, so if you have cosine squared x, that's the same thing as 1 plus cosine of 2x over 2. And if you have sine squared x, that's the same thing as 1 minus cosine 2x over 2. These are useful in Calc 2 for like tricky trig integrals, and then some moments of Calc 3. Okay. But yeah, there's technically 6 plus 3 plus 2 plus 2 that you should know. You don't need to know the rest. All the other ones don't worry about as much. Okay, so just use trig identities to reduce these down to a single trig expression. I can do that. So this is 1 over, I like to just write things in terms of sine and cosine. This is the same thing as 1 over sine and then times sine x over cosine x. Here you can just see the immediate cancellation. 1 over cosine is just secant. This is sine x times cosine x over sine x. Sines just cancel, so that's cosine x. This one, let's write this as, it's a little tricky. How about we write this one as 1 over cosine, that's the secant, and then times cotangent x at first for the reciprocal of tangent. And then that is 1 over cosine x times cosine x over sine x. The cosines cancel, you get 1 over sine, and that's just cosecant. And then now we're going to do some practice with the Pythagorean identity. So that was a lot of quotient identity and reciprocal identities. Now it's Pythagorean. So 1 minus cosine squared, if you just simply subtract off the cosine from both sides from the Pythagorean identity, it's sine squared. So this is sine squared x over sine. That's like x squared over x. One of the x's cancel. This is sine. Same thing over here. If you have, well, secant minus 1, that would just be tangent squared. So you have cotangent x times tangent squared x. That would be 1 over tangent. That's just a reciprocal identity times tangent squared x. Tangent squared over tangent is just tangent x. By the way, something minor is that you'll see I'm always carrying my x along with. For some reason, it's like a common bad habit to drop the x. I notice when teaching calc that students do that. I don't know if you were able to do that back when you were doing trig identities, but you can't do that really much anymore. That I'm personally a little picky on. I think most people are too. I don't think I'm alone on that. It could be, but I don't think so. Just the tangent of what, because if you just have sin by itself, it's the sine of what? You have to, the sine of the variable x. Okay, here I can factor out a tangent. So then I get cosecant x minus 1. And then cosecant x minus 1, that would be this identity right here. That is just cotangent squared. So this is 1 over cotangent x, cotangent squared x. Cotangent over cotangent is cotangent x. So we managed to see sine, cosine, tangent, cosecant, secant, and cotangent. Not too bad. Okay, we're almost there. Chapter 9, additional function concepts. Doing great. Okay, there's just some other small ideas that I didn't really know where to fit, but are useful in calculus. So covering these. So yeah, with polynomials, I guess I could add this in the polynomial section. Whatever. So here's the thing. We know that this is a parent function. It's just a line. We know that this is a parent function. It's just a parabola. You know that this is a parent function. It's the cubic. Oh, but I made it negative, so it's reflected across the x-axis, right? And then this one's the quartic that is reflected across the x-axis as well. Okay, so here's the thing. Your leading coefficient determines how your polynomial behaves towards the ends, the arrows. So for example, if you have a positive leading coefficient with an odd exponent, as x goes to infinity, y will go towards infinity. And as x goes to negative infinity, y will go towards negative infinity, right? As x gets bigger, y gets bigger. As x gets more negative, y gets more negative. Cool. But when you have a positive coefficient and then an even exponent, as x goes to infinity, y goes to infinity. So that has not changed. But as x goes to negative infinity, y will also go towards infinity, right? Because it's up, up on both sides. So this is always true of any quadratic that is leading coefficient that's positive. Now, if you had an even with a negative coefficient, well, then we'll see about how that behaves, right? It's kind of the point of all four. There's only 4 cases, right? You can either go up, up, down, 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 up, or up, down, right? So we're going to do the down, up one right now. Yes, so as x, so if you have an even power but a negative leading coefficient, as x approaches infinity, y will approach negative infinity. And as x approaches in negative infinity, y will approach infinity. And then you have the down, down option. So if you have an even exponent, negative coefficient, as x goes towards infinity, y will go towards negative infinity. And as x goes towards negative infinity, y also goes towards negative infinity. So these are good to know for long-run behavior. So speaking of long-run behavior, so what about when you approach infinity? So really, okay, what are we seeing a lot of here? We're seeing like this. We're seeing a lot of infinities, and actually the next problem has to do with infinity too. Calculus is bursting at the seams. Calculus is the study of change. It's the study of the infinite and the infinitely large and the infinitely small. So really, right now we're looking at problems that explore the infinitely large. We're going to be looking at infinitely small stuff too, but this is where we really are passing the buck over to calculus for a lot of these. So order the following functions from fastest growth rate to slowest as we go toward infinity. Some of these work faster than others. So for example, the exponentials. They're the fastest functions that we currently know of, high school functions here. So which one's faster, 2 to the power of x or 1 over 100 e to the power of x? Well, if you remember what e is equal to roughly 2.7, which is faster than 2, even though the 2 gets a head start, right? Because we're dividing our start by 100. Doesn't matter. 1 over 100 e to the x is still faster than 2 to the power of x. Next comes the polynomials. So for our polynomials, here's a polynomial, here's a polynomial, here's a polynomial. Oh, actually, I missed this exponent, exponential. But it's 1.01 is smaller than 2, so actually that was next. So 1 over 1,000, 1.01 x. So even though this exponential gets a significant disadvantage with this 1 divided by 1,000, still is going to beat all the polynomials. So for polynomials, we go by power. So we see this 1/10 x to the third. That is faster than 10x squared, even though it again starts with an enormous advantage. X squared is actually 100 times bigger at 1. But doesn't matter because the cube ends up eventually surpassing it. Doesn't matter that this coefficient's much smaller. Even with 100x, doesn't matter. I think that's all 3 there. Next is radicals. Those are not quite that fast, but they still make their way to infinity. So we have, I see these 2 right here. So when your power is between 0 and 1, but non-inclusive. So which one's faster? The square root of x is x to the 1/2, which 1/2 is larger than 1/3. So even though this gets a 1,000 times factor, it's still going to be slower on its way towards infinity. It'll catch up. This x squared will catch up to the 1,000 x cubed at some point. I don't know when. All right, the last 2. So the natural log makes its way to even though, man, it's got a huge head start there. Look at that 1. Man, there's too many zeros. 10,000. Natural log x. Natural log's too slow. It's the exact inverse, but it makes its way towards infinity though. The natural log of big, very, 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 very big, is still going to be very, very, very big. But the problem is sine. if this were to be a race, you would have all the exponentials that are the athletes that book it towards infinity. You have the polynomials that, I don't know, they're in shape. You have like natural log and the radicals that are really taking their time. But you have sine, who is just running in circles at the starting line. So even with that, I don't even know what that is. 100,000 as the leading coefficient. It's just jumping up and down from negative 100,000 to positive 100,000. Negative 100,000, positive 100,000. And it's just doing that forever. In the face of infinity, 100,000 ain't nothing. So 100,000 here doesn't do a whole lot. And then sine x. So this actually doesn't even make it. We're going to give it a does not finish because it doesn't make it to infinity. Just kind of keeps running back and forth. The other ones do. All the other ones do. So what's the hierarchy? Exponentials, polynomials, radicals, and logs, and then your sine function doesn't really make it too far, and neither does cosine. We don't really, like, you might be thinking, what about tangent? What about like the rationals? We don't really, those aren't going to be as important. Deal with them that way. Okay, average rate of change. We mentioned the infinitely large. Follow me here because I am going to be talking about the infinitely small now. Average rate of change is just slope formula. So if you're like, what the heck is going on? I've never seen this before. You may not have. This would probably only be covered in like a pre-calc. But it's not that crazy of an idea. It's just rate of change formula, which is y2 minus y1 over x2 minus x1. That's why, I mean, you're even seeing it within the review. That's why we started the review this way, because lines are still important. Slope is still important. So I'm going to do that. So consider the following. I have x squared. And I really just want to find its average rate of change from 1 to 3. What is this like average slope that it experiences? Because the slope changes along its journey from 1 to 3. And I realize it is connected to 0. So I don't know, 1 to 3 is like that. So yeah, like something about the line is that it has a constant rate of change. It has a fixed slope. But any other curve that isn't a line is not going to have a fixed slope. It's going to be curvy. And it's going to have, well, slopes that change during its ride. So that's where average rate of change can be useful. It's just a way to get an idea of what the experience change is. So here we would say the AROC, the average rate of change, is equal to, so really you would write it as f of b minus f of a all over b minus a. That's the official average rate of change formula that stems from slope formula. So here it'd be like f of 3 minus f of 1 all over 3 minus 1. So that would be 9, because the function's x squared, minus 1 over 3 minus 1. Do not cancel those ones. Remember, save those kittens. We got 8 over 2, which is just 4. Now what about the cubic? We just talked about how the cubic's a little faster, so this should have a faster rate of change now. This is going to be a rock. 27, because 3 cubed is 27. 27 minus 1 over 3 minus 1. And hey, look at that. We're getting 26 over 2, which is a slope of 13. So its average rate of change from 1 to 2 is roughly a slope, not roughly, is a slope of 13. 13 over 1. 13 over 1. Obviously, it changes during that duration, but its average is 13. All right, y'all, we are pushing through. Got to tell yourself that, right? Keep going. So for this next one here, average rate of change is f of 3 minus f of 2 all over 3 minus 2. So that will be 9 minus 4 over 3 minus 2. That's 5. Think about that a little bit. It should make sense that it's a little bit bigger of a rate of change because the rate of change that occurred from, what was it originally, 1 to 3? Okay, now we're going from 2 to 3, which is, you know, it experiences a greater and greater slope as you go along the journey, so it makes sense the average went up. All right, and then what about from 2 to 2.1? We're almost kind of like honing in on what not the average rate of change would be from like 2 to a value, but what the instantaneous rate of change could be at a value. Making your interval infinitely small, comparing to the infinitely big. Okay, so this is all the study of calculus here. I mean, really just we're at the door of it. Anyway, so this would just be a rock. So same business, f of 2.1 minus f of 2 all over 2.1 minus 2. F of 2, I got to use a calculator. It's the only time I got to like literally use a calculator. 2.1 squared. Man, what is that? What is that? 4.41. Okay. 4.41 minus 4 all over 2.1 minus 2. So that would be 0.41 over 0.1, which is yoink, yoink, 4.1. So slightly faster slope than if you went from 1 to 3. Should make sense because you're a little bit further along in the interval than 1 to 3. You're from 2 to 2.1. You know, maybe take a guess as to what the instantaneous rate of change could be. All right, and that's what calculus is about. All right, the last little section here, I didn't know where to put this. So there's a difference between a function, a sequence, and a series. Function is generally continuous. Sometimes you can say a discrete data set is a function, but not really in this class. So we're just going to say a function is a continuous kind of curve. We're going to say a sequence is just like data points, more or less. They're just sequential terms. So A1, A2, A3, A4. And then a series is a sum. So you would just, you would take a sequence with sequential terms and you would add them up from whatever your starting index might be to wherever you end. So if you want to add up terms of a sequence, you would use a series, sigma notation. Big E. Okay, so write a rule for the nth term of the following sequences below. So a sequence, we generally use a sub n for that notation-wise. Looks to me like it's plus 3 every time. So we take 2, and then we add 3 every time. We generally start with the first term of a sequence instead of like the 0th term. So instead of doing 2 plus 3n, we usually do 2 plus 3n minus 1. And think about how that makes sense. If I were to plug in 1, 2 should come out. If I plug in 2, 5 should come out. If I plug in 3, 8 should come out. Same story over here. This appears to be multiplied by 2 over and over again. Oh, whoa. We're going to change that. I see what I did in my brain, though. All right. Get this thing out of here. Okay, like I said, this appears to be multiplied by 2 over and over again. So, since it is multiplication of 2 through and through, we're going to say start at 3 and then multiply by 2 to the power of n minus 1. So this is known as an arithmetic sequence, and this is known as a geometric sequence. You don't really need to know those words. The big thing is, okay, so what do you need to take away from this? Is a sum, which we're about to get to. Understanding sigma notation is going to be important. This is a for fun moment. This is a well-known sequence. 1, 2, 3, 5, 8, 13. What is the next one? 20-something, 21, so on and so forth. This is known as the Fibonacci sequence. Actually, if you take a ratio of this, if you take the limit, introducing some calculus, of the ratios of a Fibonacci sequence, you get phi, which is that 1.618 value that we had earlier. All this is extra. The limit is calculus. You'll need that. But what I'm about to write, this is a recursive sequence. Nah, this is just me being extra. You just take the previous. So if you're like, what the heck is this sequence? What is he talking about? You just take the previous 2 numbers. So 1 plus 1 is 2. 2 plus 3 is 5. 5 plus 8 is 9. 3 plus 5 is 8. 5 plus 8 is 13. You just take the previous 2. So here, 13 plus 21 is, don't beat me to it, 34, so on and so forth. So you just take the previous 2 and you add them up. The previous one and then 2 prior. You don't need to know this. This is the Fibonacci sequence. You do need to know that series are the sums of sequences. So speaking of series, the way that we read this, it's the sum starting at the first term, the a sub 1 term, of this series, of this sequence. So a sequence is on the inside of a series. And we're just going to be taking the terms from 1 to 5. So here, if I plug in a 1, just a 5 shoots out. If I plug in a 2, a 9 shoots out. Plug in a 3. Wow, brain is not working. 13 shoots out. Then a 17 shoots out, and then a 21 shoots out. So instead of it being like a sequence with commas between each of the terms, it's a sum with, addition signs in between the terms. So here it stops after 5 terms total. It starts at the first term, and you go up to the 5th term. So we end it. This just comes out to 65. Here, this is a geometric sequence here. We're starting at the 0th. Sometimes you can start at 0. You can start at whatever index you want. You can go to any index you want. I could have went to 100. It's just not practical to go that high. So this would be 2 to the 0th, which is 1, plus 2 to the 1st, plus 2 to the 2nd, plus 2 to the 3rd, plus 2 to the 4th. And I don't know what that is. Wait, 1, 2, 3, 4, 5. I went 1 too many. I did not go 1 too many, because it would be the 0th term, 1st term, 2nd term, 3rd term, 4th term. Yeah. Okay, we're good. We went from like the 0th term to the 4th term, which is why there's 4 terms here. And then here we went from the 1st term to the 5th term, which is why there's 5 terms here. 5 terms here, 0, 0, 1, 2, 3, 4. And then here, 1, 2, 3, 4, 5. Okay. I got tripped up here. I'm actually a little loopy right now. I'm not going to lie. I've been doing this for almost 5 hours. I don't know. I took little breaks. So anyway, yeah. We're chilling here. So 1 plus 2 plus 3 plus 4 plus 8. That's equal to 15, right? Because that's 7. It's 15. So 15 plus 16 is 31. Okay, and then the last one, so you plug in 1, plug in 2, plug in 3, plug in 4. That's it. There's only 4 terms because 1, 1st term, 2nd term, 3rd term, 4th term. That's it. And actually, check this out. One plus 2 plus 3 plus 4, that's equal to 10. These are known as triangular numbers, which are bowling pins. So it follows this sequence. Series. There's a difference between a sequence and a series. A series has sigma notation. Sequence, just a list. Sequence, a list. Series, sum. This is big, important in Calc 2. It's small, important in Calc 1. And not at all important in Calc 3. Okay, last one. So we already did function stuff. My computer's like it. We already did function stuff. So eventually plugging in x plus h will be important. Like the first week or two of, maybe first 3 weeks of your class, you'll plug in x plus h. You'll eventually learn what that means, but not, right now we're just going to kind of black box it and just go through the motions. If I were to plug in an x plus h, in for all of these x's, so that I would replace all the x's with x plus h's. This is what it would look like. First one would be f of, x plus h. So eventually, this seems kind of arbitrary, kind of random right now, but eventually it's going to have a point, a purpose, a soul, a reason, and a rhyme. So yeah, you would plug this x plus h in for this x here. You'd replace the x with an x plus h, and then you would simplify. So here, this is a binomial. Do not distribute. Hopefully that's like the big, if you're distributing right here, there's no hope. Lost cause. Stop watching. Do something else. No. It's once you get your feet wet, you never do that ever again. This is x squared plus 2xh plus h squared. Eventually this will be important. Right now it feels very random. For this one, f of x plus h, this would be 3 over 2 times x plus h plus 1. So this would be 3 over 2x plus 2h plus 1. Can't do much more there. And then for this one, you can do quite a bit for this one. F of x plus h is equal to, unfortunately, guys, we got a binomial to a third power. X plus h to the third minus quantity of x plus h. Whew, let's get to it. This would be x plus h times x plus h times x plus h. We already did x plus h times x plus h. It was this expression. So this is going to be x squared plus 2xh plus h squared times x plus h. And then I'm just going to distribute the negative here, minus x minus h. Buckle in, because it's going to get fun. All right, so I'm going to do x squared times x, which is x cubed. I'm going to do x squared times h, so it'll be x square h. Done with the first term. 2xh times x, so it'd be 2x square h plus 2x h squared, because now the 2xh is meeting the h. And then the last distribution here, h squared is distributed both, so it'd be x h squared plus h cubed, and then minus x minus h. Woo! We are done with that problem. I'm really not that enthusiastic about it at all. I don't like multiplying polynomials. It's just like, man, I got something better to do. Do I? Probably not. Okay, done with whatever this section was called. Kind of like advanced additional function concepts, just kind of like the extra miscellaneous topics. Okay, almost there. All right, chapter 10, some geometry. Not a lot of geometry you need to know for calculus, and really not any geometry in the other classes there, pre-calc, college algebra, trig. But you need to know a little for calc. So I'm just going to cover the essentials. And yeah, that'll be it. All right, so for the first little piece here, it's important that you know that the Pythagorean theorem, a squared plus b squared, well, that's equal to c squared, right? This is in disguise the same thing as distance formula and a circle. So for example, if I just had two random points here, you know, there's some x1, y1, x2, y2, and I wanted to find this distance. Well, what I can do is I can do a triangle where this up-down different distance would be y2 minus y1, and this left-right distance would be x2 minus x1. And really, hey, if you look at that, distance would just be the square root of this, right? But it's the square root of your change of x squared plus your change of y squared. It's the same thing. Okay, and then in addition to that, if you had a circle, so let's just say you had some sort of known distance. You have some sort of point. I'll just make it the origin, okay? And you have a fixed distance. So we'll just say the fixed distance is like, I don't know, we'll just say 1, 2, 3, 4. So some fixed distance. If I have a fixed distance now, consider how if the distance is fixed and I have now control over the, you know, what the second point could be. It could be anything within a radius of that first point, the center. So it could be, you know, it could be over here, 1, 2, 3, 4. Could be over here, 1, 2, 3, 4. Could be over here, 1, 2, 3, 4. But it can also be kind of values in between as well. So it can be any of those values, can be any of those values. I'm not doing a great job drawing this shape, but it's supposed to be this thing. It's a circle. So from your center, which we'll just call h comma k, it's the same formula. It's going to be, well, here you might have some sort of fixed r radius distance, because the radius is the same no matter where you come from inside the circle. It's going to be x minus h squared plus y minus k squared is equal to r squared. So r is that fixed radius, hk is the center, and then xy we have we have some freedom in. We can be whatever we'd like for it, so long as it satisfies the equation. They're all the same thing. Understanding this is important, just like how often we see the Pythagorean theorem. We see it quite a bit in Calc 2. We see it all the time in Calc 3. Yeah. But yeah, mostly like Calc 2. Okay, and then here are the formulas you need to know for all the calcs, kind of, because like, I don't know, cylinder, cone, sphere, like some of those come into play like a big time in Calc 3. Really what I have in mind is optimization related rates, which are Calc 1 topics. So anyway, these are the area formulas I'd like for you to know. The area of a rectangle is length times width, or, you know, if it's a square, it would be side squared. The area of a triangle is 1/2 base times height. The area of a circle is pi r squared. And the area of a trapezoid, you can think about this as either 1/2 b sub 1 plus b sub 2 times h. You can either think about this as like a pseudo triangle where it's like 1/2, the 1/2 is the 1/2. Instead of it just being a base, it's base 1 plus base 2, and the height is the height. Or you can think about it as like a pseudo like rectangle sort of, where it's like the average of the bases times the height. So it'd be like the average of the bases would be like your L, and then your height would be like your W. Doesn't matter to me, but you'll use trapezoids quite a bit in Calc 1. All right, perimeters. So there really isn't a perimeter formula for triangle and trapezoid. That's why they're shaded in red. I just wanted the symmetry here. It looked nice. So for a rectangle, we have 2 times the length plus 2 times the width. And obviously the square equivalent is just 4 times the sides, right? Yeah. We don't worry about triangle. It's just the sum of the 3. For the circle, this is actually the circumference, right? It's a perimeter. So I actually don't like how I used that A there. We want to change that to a P for perimeter. And you could use P here for perimeter as well, but it's more commonly called the circumference, right? So this is going to be just 2 pi r. So we saw that with the unit circle. And then trapezoid, you just add up all 4 sides. It's not a fancy formula. Oh, by the way, the dimensional analysis of it, 2D. So the product here is of 2 different variables. Product here of 2 different variables. I mean, here you have a product. It's r times r. It doesn't matter that they're different. It's a product of 2 variables, okay? Here, this is a product of 2 variables. You get some sort of number here, and it's a product with some h value. So these are all products of 2 variables. You can kind of think about it as. Whereas with 1D, it's just 1 variable. 1 variable plus another variable. 1 variable, 1 variable. For 3D, you're going to have product of 3 variables for all these. And then for surface area, so instead of volume, surface area, you go back to area, which is 2D, and that should be product of 2. So that dimensional analysis is important for calc as well, whole calc series. So this would be the area. No. Gotta stop right in A there. We're gassing out here at the end, folks. Volume is length times width times height, or in the case of a cube, it is side cubed, right? Side squared for area of a square, side cubed for a cube. For the cone, this is volume 1/3 pi r squared h. So you got your 3 variables there, r, and h. For a sphere, it's 4/3 pi r cubed, r, and r. And then for a cylinder, it's pi r squared h. No coefficient, r, h. All right, the last problem. I was about to scroll down with my space bar. I was like going to scroll, and then I was checking out. Yeah, the surface area formula. We don't really have to worry about surface area of a cone. That weird like conical piece of it makes things kind of confusing. But for a rectangular prism, I mean, this one's not too bad, right? This is just so for surface area, it's just gonna be what, 2LW plus 2LH plus 2HW, or in the case of a cube, it is there's 6 faces, 6 sides squared. Almost done. Cone we don't got to worry about for this one. Sphere surface area is 4 pi r squared. So 2 variables, right? These are all 2. Length times width, product of 2. And then for a cylinder surface area, you got 3 surfaces here. You got, I don't know, I'll just color code a little bit, I guess. You have the top circle, you have the bottom circle, and you know the areas of circles are just pi r squared, so that's 2 of them. So 2 pi r squared. And then you got the cylinder as a whole, right? Which I'll do, I guess, in blue. You have this like whole rounded out area. Think about if you had like wrapping paper. It's usually in a cylinder. You unravel it. It kind of behaves like a rectangle at that point, right? So the height would be just the height of the cylinder, h, and then the length, that like bottom piece, the base, would be the circumference. So that's 2 2 pi r. We already saw that. It's right here. So to kind of wrap this up, it's just like a length times width. It's a rectangle. So it's the 2 pi r, which is the circumference. I'm not changing the color here. Times this height h. Yeah. That concludes my preparation for Calculus Bootcamp and Pre-Calculus College Algebra Trigonometry Crash Course Muscle Emoji. Have a good night. Please continue to math on, and I will do the same. I'll see you in the next video.